Presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. This show is funded by supporters on Patreon and Subscribestar. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Good afternoon, everybody. I hope everyone's having a wonderful day. I want to welcome you to the stream here today. So this is going to be the first time since in a while that I've done a live lecture with you. In particular, I'm going to be planning to do these much more regularly here on the channel. In particular, you'll find that I'm going to be starting to go through a lot of the content that I've been going through in the past, but I'm also going to be building on top of that. So for example, there'll be more videos on, for example, Big O Bootcamp. There'll be more on data structures and algorithms. Most certainly some that we may have had on the channel before, but I want to I guess enhance these and also update them. So you may find that some of the content is going to be stuff that I've covered before, but enhanced. Other stuff will be brand new. Now, you can always have a say in what I'm covering right now. You can always, of course, check out and subscribe, follow, tell your friends to come on down. I'm offering you an affordable and accessible way to learn computer science on your own. Or if you're an interested computer science student and you would like to learn this stuff in another way, this is another avenue for learning this stuff. I know that I've been teaching computer science for a number of years, and students tend to usually have a good time with me. So anyways, let me just see what's going on over here just to see. Okay, so we got a couple people watching. That's pretty good. Do keep in mind, I have the chat open here on my monitor over here. So if you have any questions during the Big O Bootcamp, which is going to be what I'm going to focus on today. And keep in mind that I'm going to be doing multiple sessions of these. So this session will be dedicated to introduction. So I'll be doing the basics that I would usually go through with like a data structures course. In particular, I'll be focusing in on big O notation because oftentimes students, especially those from computer science, sometimes there's this kind of disconnect between what big O is about versus what an algorithm is about. We're going to focus on the big O part here. Big O is a rather useful and effective way of expressing the running times of algorithms with respect to the input size for many, many instances of a given problem. So I'll be focusing in on this. So like I said, if you have any questions during this process, of course, let me know in the chat. Let me know how you're doing in the chat. Let me know if you're out there. If you're having a good time, let me know in the chat. I'm really happy to hear about it. So of course, in between each one of the examples I'll come back to here to ensure that we're obviously all up to speed. But at the same time, also, if you have any questions during this, feel free to put them in the chat and I can address them at the end of the example. If not, if I see it's something that I can elaborate on that spot, I'll happily do it. So another thing I need to mention is if you find yourself wanting to get access to any one of the notes so for example, today I'm going to be covering Big O Bootcamp. The notes for this session will be available along with the other sessions I have prepared so far for Big O Bootcamp are all going to be available on my Patreon or Subscribestar. You go to patreon.com/pagewizard. You can find all of the resources that I'm covering here. But keep in mind that I will be doing all of it here. So everything I'm talking about here will be available regardless, because like I said, I believe very strongly in affordable computer science education for everyone. So anyways, with that being said, why don't we get started, okay? Sorry, I'm getting very excited here. I'm just like losing it. So I hope you're having a wonderful day. I think I got everything I needed to. So that being said, I guess I should get started. So that means if it's Big O Bootcamp, it's fashionable that I make sure I got my Bootcamp hat on. Let me get that on. There we go. There we go. Perfect. Perfect. Just got to make sure I got this on right. Otherwise, I'm going to fling it off somewhere. So let me get us going here then. So I'm going to start off with talking about some preamble. So this will be kind of the setup for what we're going to be doing here today. So this is also for people that have never heard or seen a Big O notation before, so you have an understanding of what I'm talking about today. Woohoo! Yes. So we're going to be doing, so first going to go through a bit of a preamble, and let's get in on this, okay? So before anything, I like to make sure you have an idea of what exactly we're talking about today versus what we're not talking about today. So I'm going to be focusing in on a key tool or mathematical tool that we use for describing complexity for algorithms. So what's complexity? These are the resources, the amount of resources needed to solve a problem with an algorithm. So I thought I would give you an idea of just where exactly we are in this process. So usually when you study a problem, normally when you're using some model of computation to measure how many instructions or how many operations are happening for your given algorithm, you perform these kind of key processes. So usually the first thing you do is you present an algorithm. Now keep in mind that this algorithm may be correct or incorrect. So we're not going to be talking about this. So remember that an algorithm may or may not be correct. That's not what I'm going to talk about here with you today. Today I'm going to be focusing in on a specific part of this. So once you have an algorithm, normally you would like to analyze it. So for example, proving its correctness, meaning that we can guarantee that whenever you give it input, it always produces the correct output. So usually the next step after this is you try to analyze its complexity. Remember, like I said, that is the amount of resources that the algorithm needs to perform the computation. So usually people measure things such as space complexity, so how much memory gets used by the algorithm. You may talk about time complexity. That's a very common one, the amount of time it takes. Normally this is measured in operations based on what you're using as your model of computation. So people use, for example, the random access machine model. Some people use Turing machines to do this. I'm going to focus I'm not really talking so much about that here, but the point is that you decide on some analyses. So you just decide on a type of analysis. So once you have kind of a model that you're analyzing the algorithm, keep in mind, normally you develop the algorithm for the model. So if we're talking about general purpose computer models of computation, then that would have been done in step 1, because you have to describe the algorithm in a way that is understandable or translatable to such a model. So when you're determining the type of analysis, people measure the complexity in all sorts of different ways. For example, worst case, average case, best case. But when they do this, what they do is they count up the number of operations that happen in a particular way based on this model. So once you've done this, when you count up these operations, you derive something we call a complexity function. So you derive a complexity function for the algorithm's analysis. So that's the third step. Now, notice that if you do this well, then it will reflect the complexity for the given algorithm. Now, like I said, this entire process is, okay, I give you an algorithm, I do some type of analysis, I decide on the analysis, what I want to investigate about the algorithm, or which gives us some insight into the problem, usually. And of course, we derive this complexity function. So this complexity function measures the complexity for a given size of the input. And then naturally from here to this last step is to determine what we call the asymptotic behavior of complexity function. So this is step 4. Normally this is expressed in what we call the big O notation. But there's other kinds of asymptotic notations. Now, what we're going to focus on is right here. So we're going to be presuming we're given some complexity function that measures the complexity of some hypothetical algorithm. And then we want to determine its asymptotic behavior. So normally we would like to have some complexity function. I would like to prove its big O, which we're going to talk about what that is today. So we're going to look at where this squiggly arrow, I thought it was a little fun to make it squiggly. What exactly happens here? So that's what we're going to focus on here today. And that's what the focus of the Big O Bootcamp is what exactly do we do? Like, so how can we prove that we have a given complexity function? How do we prove to somebody that it has a given asymptotic behavior? So for example, if I give you some function like big O, like say if it's like n, I want to show you that it's what we call big O of n. But I would need some rigor to do this. I can't just simply just assert it to you and you just kind of say, trust me, bro, it works like that. That's not how this goes down normally if you're dealing with formalisms here. So that brings me to defining a couple things. So first, hopefully this is going okay so far. So just remember, this is kind of like where we're at. So we're just going to look at that one step. All of this would be a complete picture for an analysis of algorithms class. But I'm going to focus only on this step because usually students have difficulties focusing in on this step. But at the same time, it gives you some insight on how you can measure growth of a given function, but also how you can think about a whole class of functions and see how they're interrelated as the input gets large. So they belong in these little bubbles or buckets, as we're going to see. So another thing I need to define for you is something called a complexity function. So you know how I talked about this idea of deriving a complexity function? I got to define that for you. So there's going to be a definition I'm going to use. This is our working definition for a complexity function. Remember, this measures the complexity of the algorithm, the resources that algorithm needs to perform the calculation or the computation. So let me give you a definition for this one. So it's going to be what we call a function f on the domain. So don't worry, I'm going to draw you a fun picture. I am a big fan of fun pictures. On the domain of positive integers, to non-negative real numbers. So for those that really like so-called mapping notation for functions, what I'm telling you is that this function takes as input a positive integer, and as output, it spits out a non-negative real number. So these are real numbers that are 0 or larger. So just as a reminder what a function is, I like to draw it in terms, I like to think of it like a machine. So imagine you have this funky machine. I don't know what this function, it looks funny. So what it does, it takes an input in the top of it, and it spits out a result that the machine will compute. Goes through some process, I don't know what it is. Whatever the complexity function is defined to do. So in this case, what it does is it takes in a positive integer. That's what this fancy Blackboard Z with the plus means. It means positive integer. If it doesn't have this plus, it means it's just an integer. So these are numbers like -2, -1, 5, 7, and 0. Those are integers. Positive integers only includes 1, 2, 3, 4, 5, your typical counting numbers. This is in contrast to non-negative integers. These are 0, 1, 2, 3. It includes 0 in there. So I put an integer in, function f, that's its name, will then perform some calculation, and as output, it produces me, like say if this is n, so suppose I called that n, the input n, it spits out f of n, which this right here is a non-negative real number. So that means that we're talking about numbers like 0, 1/2, pi, things like that. So this is what we're going to refer to as a complexity function, but I must stress as a convenience, sometimes I'll define the domain, meaning that's what our inputs for this function are. I'm going to sometimes allow it to have the value 0, even though it doesn't make a whole lot of sense from the standpoint of the input of an algorithm. Sometimes it actually does. So if you think about it as like, oh, the size of the input, okay, well, what if I give you no input? Now, typically when you don't have any input, there's nothing really to compute, right? But the thing is that sometimes I would like to express the complexity function in terms of itself, what we call recursively. And sometimes it's helpful to have the ability to define it for the input when it's 0. Theoretically speaking, it doesn't make any difference from a big O standpoint, but it just simply is a convenience I'll be using, not today, but some point in the future. So are there any questions about this? Does this seem pretty darn clear? So just as an example, a complexity function can be something as simple as like f of n is n. You can also have other functions like this. Like you can have what we call a constant function. Say f of n is 5. And keep in mind that the name f isn't special. You can call it something else like g. So I can have g. I can make this n squared plus n. So just keep in mind that f there is the name of the function. But very often when I write this out, I'll be specifying its input here. Although technically speaking, the output of the function is called f of n. I'll usually be writing this out regardless, just to keep it easy so you can see what the input is. It's a shorthand, but it is an abuse of notation. So I must stress that there are other ways you can define what we're going to call the big O notation. For example, it uses something like using absolute values and things like that. I'm not going to focus on that definition here because it's not really going to add too much for us from a computer science I'm getting very excited here. A computer science standpoint, it doesn't really add anything for us. Because keep in mind, a program cannot perform negative number of operations, okay? It's not like the computer, you're like owing the computer an operation. So you can imagine like a computer program that performs operations for some sized input. It performs some operations. It doesn't have the ability to just perform negative operations. It's just a convenience when you want to talk about general functions. And that's why some people define it like that. I will not be doing that here. It doesn't really add a whole lot given the fact that most complexity functions that you actually study in computer science do not really need that. because most complexity functions you're going to run into have a very specific structure to them, including the fact that they're programs and they perform operations. And when I count those operations, they're always going to end up being some non-negative number. So a program that does nothing, for example, which is very strange, by the way, to imagine, that, for example, performs 0 operations, but such a program is very hard to conceive of. If you think of it like, okay, the program still has some operation it has to do. It has to obviously tell you to stop computing, right? Well, that's still an operation, right? It's kind of weird to think about. But you can think in a theoretical sense of such a thing existing. So anyways, it's also a convenience for us because some of the functions that we're going to look at have it where they spit out for the smallest inputs the value 0. For example, logarithms have such a thing. So for example, log base 2 of 1 is 0. So that's also another reason why I've restricted the definition like this. It's very common in computer science circles. So are there any questions out there? Don't be shy. I'm really happy to answer any questions. So far, we're doing okay? Okay. So let's proceed. I'm going to now talk about the definition of big O. And I'm hoping that I'll be able to give you some idea of what this definition is. Awesome. No, good. So we're going to be heading over here. And we're going to be talking about the definition of big O. And I must stress that big O is very commonly used in algorithm analysis, and when people talk about different algorithms, they usually talk about the running times in terms of big O notation. So this is also for several other reasons that I won't go into so much here, but the point is that regardless of the implementation of the algorithm, you can find out when you count up the operations that are performed, it always falls into some bucket of functions, and the big O is effective at capturing this. So yeah, I'll give you some insight into this as we go along, but it's not really the focus here. So I'm going to first talk about the definition of big O, because it's probably a good place to start. Now I must stress that this notation is something that birthed more out of analytics from mathematical analysis. So it was not primarily developed for algorithm analysis. This is something that came along later. So sometimes people refer to big O notation as Landau symbol, named after one of the mathematicians that popularized this notation. But I must stress that its definition did evolve over time with Donald Knuth and others of the sort. But anyways, it's a kind of what we call asymptotic notation. As the name suggests, it means that the input as it gets big. So you think of it as things get big, this is what you would expect the function to behave like. That's how you could think of what I mean asymptotic, as it gets large. But keep in mind it has a double meaning in the world of computer science. For example, like I said, you could think about it as the scaling of how well the algorithm scales. So for example, if you have very large inputs, like say for example, your algorithm is computing on an array, like if it has only 10 things it has in this array versus 10 million, it makes a big difference if you have a very slow algorithm versus a rather fast one. I'm not going to talk too much about fast versus slow here, but you can get an intuition that the big O notation will be helpful for discerning a fast algorithm from a slow algorithm if you wanted to compare two different algorithms when the array, for example, is 10 million elements as opposed to just 10. But also, another reason why is because it captures all of the inputs for a given problem at the same time. That's another reason why the big O notation is helpful. You can think of it like just a nugget that you could present to somebody and say, this is the complexity of the algorithm right here. And I could describe it in terms of the input size. So that's the way I usually like to prefer talking about it. So I'm going to define, so when we talk about what a complexity function is, I'm going to let f and g, in the truest way of some sort of thing like this, I'm going to let them be called f and g. They're going to be complexity functions. And I assure you I'm going to draw some pictures and have some fun demonstrations here shortly. So let's get in on here. So be complexity functions. So when I write f is big O of G, this is equivalent to me writing the following. Now, very often in logic, we'll say this is if and only if. So that means that if I say that f is big O of G, it must be that whatever follows after this if and only if also has to be true. If f is not big O of G, then whatever follows after this if and only if isn't true as well. So that's how you just need to think about when we talk about this. They're equivalent statements. That's what I'm trying to tell you. Is that if this is true, then this has to be true. If that's false, then this has to be false. Okay. So let's talk about this. So if and only if there exists. So you're going to see that I'm going to describe this in a way that's also going to sound like a game of sort. That we're going to try to figure out some of these interesting numbers here. So watch. There exist positive real constant. So this is a positive real number. So a positive real constant C. So we're going to call it C here, but I must stress you can call it whatever you want. If you want to call it Bazooka Jim, if you want to call it Miss Kitty, you're welcome to do that. It's just that I'm calling it C in this definition for the sake of convenience. And a positive integer constant. Integer constant. And 0, so this is, let's say, numbers like 1, 2, 3, 4. It can't be 0. It's a positive integer. So we're going to call it n0, such that for all n greater than or equal to n0, it has to be that f of n is less than or equal to c times g of n. So sometimes when people describe this to you, sometimes people use the phrase f is big O of G. Some people will say is in as opposed to is. There's a meaning and reason for that. Some people also say f is order of G. But so let me give you an idea what I mean by this. So in the plain language, let me just draw you a picture. I'm going to draw you two pictures. They're going to be kind of cute and small. So these are a couple helpful pictures for this. So imagine that I have a linear function. Ooh, that was a little squeaky. We have a linear function here, and I have a quadratic function like this. I could draw straight lines. I know, right? Amazing. So suppose that this is f, and this is g. And suppose I have another function here. Say, I don't know, one that kind of wiggles around a little bit, and then goes like this. Does the wiggle, okay? And then I have another function that goes like this. And suppose we're considering as the input gets large. So let me just get out of the way here. So I have f and g. So I have this first picture here. So anyways, we have f and g here. And as n gets large, you're going to notice if I look at my first picture, if I look at the line that, this parabola that plots out g of n, notice that everywhere I look on here, notice everywhere after here, regardless if I start at 1, 2, 3, 4, 5, so on and so on, notice that the g curve always is above the f line, right? That's always the case. So notice that in this case, if I were to look at this function, it wouldn't matter if I were to make, say, C1, 2, 3, 4, 5, 6. But notice that I could imagine this just being one function times some constant. And everywhere after, say, 1, everywhere after this, if I look just after this line, every time c times g of n is always going to be larger, it's going to dominate f everywhere after this. So notice that this line, this curve is always going to be above the line. Something similar happens over here. Just to be a little bit clear, I'm going to call this c times g of n. I don't really know what c is. I'm just drawing you a fun picture. So notice here that for smaller values, the f curve goes above the g times c curve. Does everybody see that? Just for a little bit, right? But notice that after that point, presuming that these are the behaviors of these functions afterwards, so this one keeps going up this way much quicker than, say, this f curve does. If I do that, notice that if I look at this point where these two intersect with each other, notice I can pick here or anywhere after here, and notice that this curve, the g-related one, is always above the one with the f. So just to keep this dramatic for you, let me grab my pointy sticks. Okay, that was a little loud. I shouldn't do that right close to the microphone. So if I look at this, notice that everywhere after n0, my one right here always stays above the one to the right. That was brutal, I'm sorry. But I could do the same thing here. Notice that everywhere after the top one, it never goes and crosses ever again. That's the big thing. And yes, I'm coming in for like a fatality or something here. So anyways, so this is just so the key things I want you to identify from this definition are that the game is simple. And I usually like to call it the game plan. Is notice that the definition says that there exist these two constants, the c, and this positive integer constant n0. So as long as these two constants exist, such that they satisfy the following property, meaning that this inequality holds for all n greater or equal to n0. So after that point that we've identified, which keep in mind it could be that point or anyone after it, say for example my two pictures, keep in mind, these are not proofs or anything, they're just examples. I didn't even define what the functions were. You just sort of look at the behavior and we made presumptions about them. But notice that everywhere after the line where I put n0, it would be the case that this inequality would hold under our presumptions. So just remember, the game is as follows. You gotta find this constant and this constant. You got to find those two such that f of n is less or equal to c times g of n for all points after and including n0. So you get to pick these two constants. Sometimes they exist, sometimes they don't. If they don't exist, then most certainly, based on the definition, what I just said, it can't be that f is big O of g. So I thought I would show you just a couple of ways people use big O notation. But are there any questions about this definition? Keep in mind, I'm going to do some examples actually using this in a moment. I just want to show you a couple of use cases, so like how you'd use this notation. And I must stress that I will be going through other asymptotic notations as well. And also I'll be showing you some other techniques that normally in, say, a typical CS class, you will not have enough time to go through thoroughly. So I tend to like to show some of these beyond that. So you might find some of these little, I wouldn't call them necessarily tricks, but most certainly properties that asymptotic notation have. Some of these you'll find very helpful if you're finding good like shortcuts for doing calculations. So anyways, if there aren't any questions, I'm going to proceed to talking about usage. So let's get in on this, okay? Oh man, that was loud. I shouldn't do that right in front of the microphone. So let's let me talk about a couple ways that people typically use big O notation. These aren't the only ones, but I'm only going to be talking about, again, like I said, within the context of algorithms analysis. So, say for example, in like analytic number theory, you might use these slightly differently. But each one, I would argue, has its own place for how you might use it. So, a first example I would like to do. So I'll just go 2 common usages. So the first one is in terms of set theory. This is the one that I usually recommend if you want to get a feel for how, you know how I talked about how these functions organize themselves like in the buckets. Now the neat thing about big O notation is that it isn't just simply separate buckets like this. It's actually that buckets nest within each other, as I'm going to show you in a moment. So the first thing is that some people very often write, when you say f is big O of g, they might use what we call the set theoretic in. So they use this symbol. It's a set theoretic in. They might say f is big O of g. Or they might write the n here. That's okay. Like I said, that's just to specify the inputs. So the big thing is that big O notation represents a set of complexity functions. Okay, so let's see. So just for those that are savvy with set theory, I'll just give you an idea of what I'm talking about. So if I write big O of g of n like this, the definition of big O actually says that a function is big O of g if and only if it has those two constants, right? That means that for any one function f, you can actually define it as a function or complexity function that sits inside of this set. Think about it, it's just a bucket that contains all these functions. So it contains any one complexity function f such that there exists, this fancy backwards E represents there exists. So it's just an abbreviation for our purposes, but it's just some logic for us. So there exists C, that's a positive real number. This plus just simply means positive. This blackboard R means real number, or set of all real numbers. And there also exists N0, which is a pause manager. We already had that discussion of what that means. For all is an upside down A, so this just means for all. So I may as well just write there exists here too. For all n greater or equal to n0, from your purposes, you'll most likely look at this and say, oh, this is just like an abbreviation of what I was talking about, which is true. For all n greater or equal to n0, it has to be that f of n is less than or equal to c times g of n. And I ran out of space. The squiggly is the closing of this set builder notation. So any function that has these two constants such that f of n is less than or equal to c times g of n for all n greater or equal to n0 will belong to this set. So for example, if once you get some examples seeing how to prove big O statements, you'll see very quickly that, like I said, they nest into each other. There's other ways asymptotic notations do behave, but big O is always about containment in one direction. Some people would describe this as what we call an asymptotic upper bound. And that's very often how I'll pragmatically describe big O notation to you. It's asymptotic upper bound. So for sufficiently large value of n, it has to be that regardless, it'll always be bounded by a multiplicative constant times the function. There always will be such a value such that this inequality has to hold. So we're just not really caring about a multiplicative factor on that function, g in this case. So let me give you an example of what I mean. So consider the function just where the whatever it does, it outspit 1 always. So this is an example of a constant function. Likewise, you can have functions like 5. You can have a function that spits out 10 every time. It could be some constant c. So it could be any positive real number, for example. These all, you can actually show, using this definition I gave you over there, you can show that all of these are big O of 1. So these are the set of all constant functions. So usually in the analysis of algorithms world, whenever we talk about time complexity, we'd refer to this as constant time. But you'll notice that you can keep doing this. So notice that this right here will contain other functions too. These are just examples. There's more functions in here. But you can also show, for example, that say a function like, I don't know, n, and say 2n plus 5, and say 1000n. All of these are big O of n. So they all nest like this, like a Russian nested doll. So you can keep doing this with different classes of complexity functions. And there's more of them out here. I'll discuss some of those in a moment. So having an intuition that a complexity, so you think of big O as a set of complexity functions, it's meaningful in the sense that if ever you give me a complexity function and you could show me it's out here but not inside here, this separates two different groups of functions, right? So this separates the linear functions from the constant functions. And there's other ones that sit in between these two sets, such as the logarithmic functions. So another usage that you have with big O notation is, and this is one that's very common, and this is a very common convention, by the way, is that some people will write f is big O of g using an equal sign. So I must stress that this is not an equal sign. It just means is. It's not equals, just to be clear. I know it's kind of confusing because that's an equal sign right there. But it's a convention. Like I said, some different areas adopt conventions. This one's actually a useful one. So this one right here is actually because very often when we want to simplify complexity functions, asymptotically speaking, we would like to have some way that we can group terms like in an algebraic way, such that I can discern out the stuff that's mostly fluff. That I can suppress that all inside of a big O, or I can even group big O terms like I'm manipulating algebraic terms. So this is more, I would argue, it's useful for simplifying calculations. So I'll say useful for simplifying calculations. And the biggest thing you need to be aware of is when you use this notation, you read everything from left to right. It's not a true equal sign. It doesn't mean equal to. So this is not like if you're talking about sets here, for example, like in our first usage, you would not use the equal sign in the same way. This would mean literally we're talking about sets. Like we're saying this set is equal to that set. This one is actually saying, hey, look, we're saying that all of this is big O of this. And very often the usage is that you operate it like algebra, but the thing is, you can't just simply just go backwards. You always have to go from, once you start throwing the big O in there, you never can bring it back because now you're talking about potentially other functions that are sitting inside that big O. It's sort of like it's like a snowball rolling down a hill, and as it collects up these big O terms, now you're talking about more and more stuff. And you can't really discern what you originally grouped in. I'll give you an example of what I mean by this. So this should be read left to right when you use this. So for example, say if I give you f of n, and I say this is 6n cubed plus 20n plus 8. So a couple quick tricks you can talk about when it comes to big O notation is that whenever you have multiplicative constants, you normally can just drop those. So for example, if I have 6n cubed, I can for example talk about I could drop that 6 right there, and I could get a big O of n cubed. So for example, if I have 6n cubed, then I could rewrite that as big O of n cubed. Likewise, I have 20n right here. I can drop the 20 and I could just write n. But remember, I have to put the big O there. And 8, remember, we established those are all in big O of 1. I can replace that with big O of 1 if I wanted to. But you'll notice that I'm always, whenever I do this, I'm simplifying by grouping them into all of these other ones here. And I must stress that these steps are technically not valid unless you define the big O notation to have addition and all of these other things. So some people would call this an abuse of notation because now you're playing around with sets like they're numbers. And I must stress that not the kind of numbers that you can easily manipulate as sets. So some people, you can formally go about this, but most certainly in the way people use it, it's very much a quick, fast and trick way of doing things. So for example, I can replace the 6n cubed with a big O of n cubed. I can replace the 20n with just an n. So I'm going to write big O for each one of these. They're going to suppress those constants. And remember, I'm just going to look at what the most dominant term will be when I look at this, because I'm trying to figure out the asymptotic order of the functions. So I can have plus big O of 1 So notice that if I tried to go backwards on this process, if I tried to make this like, oh, that's 6n cubed, notice that you can't just simply pull that out, because now what you're doing is now you're talking about any one of the functions that's sitting inside of this set, which it gets a little confusing if you try doing it that way. So do you see why you have to go left to right? Because remember, what big O of n cubed means is that also contains things like 8n cubed plus n squared plus 5, right? I can't just simply replace 6n cubed with that. They're not the same thing. Now, truly on an asymptotic level, it doesn't make any difference if you're trying to determine the big O, but most certainly, it's almost like I said, a snowball effect. As I'm going, I'm suppressing all of those irrelevant details as I'm doing these calculations. So notice here that the most dominant of these functions is the one with the largest exponent here. So I would just simply say that all of this is big O of n cubed. Now, you might ask, Dan, why would you have this example here like this? Well, the reason why this usage is rather helpful is because you can imagine that you're counting up all the operations of your algorithm, you're formulating your complexity function. Say these are 3 parts of your algorithm. Say this is the first phase, that's the second phase, this is the last part, the little bit of cleanup. Well, then what you could do is you can separate each one of these, compute the big O of each one, and then you just add up all of those operations in terms of big O. This is very often how this gets used, and you'll find very quickly that when you deal with very big, complex algorithms, when you have lots of bits and pieces, sometimes they interrelate with each other, so you have to be very wary when you do things like this. It could be a little sloppy, but if you have 3 distinct phases where like this thing happens, then this thing happens. Say, for example, an initialization phase, then you have like a nested loop, and then you have something where it does a little bit of a tidy up, say some number of operations, but it just simply returns whatever the result is. That would be something like this. So just keep in mind that big O is an asymptotic upper bound, and likewise that the game plan for us is to identify these 2 constants. So just remember, we're trying to find the constant C and N0 when we try to prove these claims. There's a lot of ways we can try to do this. So I'm just going to reiterate a couple of things that I said over here just once more because they're going to be rather important for us. So if I have f and g, remember, we say f is big O of g, if and only if there exists the positive real constant c, and there's also this other positive integer constant n0. So the game plan is as follows. You're going to find that whenever we try to prove claims, just to verify, you know how I went like, oh, I wrote down 6n cubed is big O of n cubed. I would like to have some formal way to be able to tell you this. So I should be able to present you a proof that confirms this fact. That's what we're going to focus in on. We're going to try to figure out how we actually can do this. So I'm going to actually give you an example that's kind of like this actually in a little bit. But yeah, just keep in mind, you got to look at, we're trying to find that point therein or after, where our g times c is always going to dominate f. So everywhere after this n0 point, c times g of n is always going to be above or matches f. So just keep that in mind. That's going to be very important for what we're going to do here. So I thought for the sake of clarity that I should just, before I get any further, I'll ask for any questions or anything like that. But also at the same time, if anybody needs to go drink some water or something, I'm going to stop for just a moment. And when we come back, we're going to start talking about different kinds of functions. And then we'll start talking about how we can pick up this definition and use it. So I'll give you like a couple of minutes here. I'm going to get back on this chat here. And there we go. There we go. So if anybody wants to ask me anything or want to chat about anything, I'm happy to do that. But yeah, when we come back, we'll just quickly, we'll go through a couple more things about these different buckets. You know how I talked about like big O of 1, big O of n? I want to give you a list of some of these so you're aware of the common categories people tend to use. Because usually that's very common in computer sciences. They normally like to lump these into these specific categories. And it's not really unreasonable or arbitrary, really. These are all just different functions with different types of growth rates. But yeah, no. I hope everyone's having a good day. Yeah, no. having a bit of a blast here. It's nice seeing some people, lovely people popping on in. Just gonna erase this board on my left here, just so I can write down some functions over here. But yeah, what we're gonna be doing today is I'm gonna do some basic examples, and then I'm gonna work up to something that's a little bit more complex. So we're gonna start off, which is some basic functions. We're gonna try proving the big O claims for those. And then, of course, after that, we're going to see some tricks you can use with polynomials. And then, on top of that, I'll be showing you an interesting, bigger example. So I'll be doing, for example, a case when we deal with I believe it's the harmonic numbers. I believe I look at the harmonic numbers, which is, I think it's, if not, it's the harmonic series. Okay, yeah, it's the nth harmonic number. Its analysis is a little craftier. It takes a little bit more thinking of how you would go about it. And most certainly it does not, we don't apply necessarily the same trickery that we can use because it's a little bit more crafty. It's actually a good example of how you get connections between logarithmic functions with counting based on how many times you can apply a given definition. But yeah, that'll be kind of the trickier one we'll go into. We'll see how far along we get along here today. If after that, what I'll do is I might prove some properties of big O for you. If not, we'll hang on to that for next time, because next time what I'm going to do, for sure, I'm going to be talking about big omega and big theta. And then on top of that, so for example, if there's anybody that's taking any analysis of algorithms classes, I know there's at least one going on right now. You might find some of that pretty useful. Then on top of that, what else? I know I'm going to be doing a proper set of discussion on smoothness. I usually like to talk about that topic because it greatly simplifies some sets of analyses you might do. Recurrence relations are something I'm going to talk about as well. Some of these things I do talk about quite often in analysis of algorithms classes, but I'll be going even further, so I'll be trying to be a little bit more thorough with this process. And on top of that, like I said, I plan to do some other tutorials as well live, so if there's any specific topics you're interested in, let me know. I'm very happy to explore other topics. So, for example, I'm planning to actually do a series on graph algorithms at some point in the near future. So right now, kind of like the big projects I have going on right now is I'm working on the second edition of my data structures book, which that has a self-learning session to it. So the book is designed for self-learning. So I'm working on the next edition of this, so I'm going to make new lectures for all of those. Keep in mind that all those lectures are available here on this channel. Just that I would argue that if you went back to them, you'd be like, Dan, the quality of these videos is not nearly the same. It's because I just started off when I was doing it that time. I was doing it in what I was lovingly calling the bomb shelter. Now we're in the learning zone. But yeah, no, what was I gonna say? Yeah, that's one of the projects. Big O Bootcamp's another. This is actually, a lot of these exercises are all going to be going together into one book. So if you're looking for like an ultimate guide to doing big O proofs, or you're looking for techniques on this kind of stuff, I'm putting together a comprehensive resource on this. It's gonna be very affordable. So I'm coming for you, CS profs that don't know how to teach this stuff properly. I'm coming for you. I'm coming for blood. I'm joking. But yeah, no. But yeah, no. So there's that. Then also I'm working on actually a programming series as well. I'm doing an introductory programming series on introductory Java programming. That was something actually my Patreon supporters had suggested. So that's a series that I'm coming back to. I did a few videos for that. So far we got up to a Hello World program. So after that, I need to start talking about things like data types, strings, and how you can do some basic stuff and conditional statements and so on.
It's a terrible topic for me while going to school.
Hey, look, it's a pleasure, of course. So what I was thinking of doing is I'm going to get back on what we're talking about. So I was going to talk a bit about those buckets, right? I showed you some examples of like how they can nest into each other like that. That's a property of big O notation that it has this asymptotic upper bound business that's going on. Some other asymptotic notations actually are asymptotic lower bounds. And then there's some that actually make it so that they separate into specific categories so that they don't overlap each other, such as the big theta notation. So anyways, let me just go into some, let me run through a list here. So I'm going to head on, actually, before we get back, I'm going to kind of recap this for everybody. So let me just get this going back here. Okay, there we go. So anyways, just as a reminder of where we are, I gave the definition for big O. I gave us an idea of where we are. So right now we're not analyzing algorithms. We're looking at the big O definition. We're going to see if I give you some function we call a complexity function. I want to know that f is big O of g, but I need to be able to give you some way to verify it for yourself, which is the best way of doing this is the mathematical proof, which at first it sounds really kind of, you'll be like, math, that dreaded M word. I assure you the cool part about this is that if you make a claim to somebody, I'm giving you the way you can reason to somebody about why this thing is true. That's the power of a mathematical proof. It gives you the Y answers. It gives you the big W. It's a win and a Y. So anyways, the game plan here is we're going to find these two constants, C and N0, but it has to be that when we pick these two constants, that this inequality right here has to hold for all n greater or equal to N0. So I must stress that a very common pitfall students fall into is they just sort of presume that if they find N0, that everything after that always behaves a very specific way. Meaning that they could just plug in whatever they pick for N0 into this inequality here. So they put in N there, and they say, oh, I'm all done. I'm all done. I don't have to do anything else. And the big problem here is that that isn't actually what this says. This says this inequality has to be true for all n greater or equal to N0. So it's actually a stronger statement than just saying that there exists an N0 such that that inequality works. You have to be a bit more careful. So often the mistake made here is that if you do something like that, you fail to justify why the inequality is true at that point and afterwards. Just like on our pictures over here. It's not just true at this N0 point, it's true everywhere after that, that C times G always dominates F. So let's talk about some functions. Let's get in on this good stuff, okay? So I want to give you some of these different categories because normally when people talk about complexity, they sort of break them into these buckets. These aren't the only ones, by the way. There's some really fascinating ones out there. So let me talk about those. So I'm going to call these common classes of functions. Common classes of functions. So the first one that we actually talked about, this one's big O of 1. So this is the set of all constant functions. So these are constant functions. So things like 5, 10, any positive real constant C, these are all constant functions. Then you have your logarithmic functions, for example. That M looks a little sad. It's about to turn into an N. It wants to N itself. Oh, that's bad. Anyways. The next we have big O of N. That's linear. Then we have big O of N log N. This is sometimes called log linear, but most people, if you ever talk to them, they'll just say big O of log N. Or sorry, big O of N log N, sorry. Most people don't call it log linear, but I've seen this term used for this. I was trying to find a label for you to describe it. I've usually seen this literature discussion when you talk about some very narrow data structures kind of research out there. Some people want to have some way of describing this too without saying big O of N log N. There's big O of n squared. So you might recognize a lot of these names if you've studied functions before. We have quadratic functions. So like I said, remember, these are sets of functions. So for example, like quadratics here contain things like 5n squared plus 5. Those are all quadratics, right? So other ones also include polynomials. So we have n to the c. So big O of n to the c. These are polynomials. So this is for any constant c greater or equal to 0. So this subsumes a good chunk of those up there. In fact, it technically consumes every single one of the ones up here. So you can actually look at this as successive nestings of functions. So big O of 1 is contained within big O of log n. Big O of log n is contained within big O of n. Big O of n is contained within big O of n log n. Big O of n log n is contained within big O of n squared. Big O of n squared is contained within big O of n to the c, where as long as this is some constant c greater or equal to 0. So you can pick the c to be whatever you want. It's some constant. So it can make it 3, and then now you have the cubic functions. And then you have some other things like exponential functions. So you have big O of c to the n. So this is exponential. So this is any constant c greater than, well, c greater than 1. I was about to write 0, but that doesn't make a whole lot of sense. It's an exponential function. Yeah, c greater than 1. So this is stuff like 2 to the power of n. The things that grow rather quickly. There's some other ones too, like there's big O of n factorial. These grow faster. And there's also other things out there, some that I don't even know what they're technically called in the literature. Just normally if you ever had an algorithm that ran this slow, you'd kind of throw it out unless your problem was really that tough. Things like big O of n to the n. I'll call it oops, okay? So anyway, so these are some common classes of functions. Normally when we talk about f and g, g is normally the function that would be sitting inside of one of these. So normally we'd like to characterize them like these, but I must stress that there's other functions too. There's some that are so strange that it's very hard to explain them to you with only a matter of one sentence. Some grow so slow, for example. There's something called the log star or iterative logarithm. For example, log star of n. For all practical values of log star n, this grows so slowly that in practice that it may as well treat it like a constant for practical values of the input. There's other ones even out there called, for example, like the inverse Ackermann function, that for up to about, I can't remember the number off the top of my head, they grow so slowly that in practice, if you were to talk about, say, 1, 2, 3, 4, 5, the numbers are still going to be so small that if you get up to, say, 10 billion, it's still going to be a number that's not going to be anywhere close to the, or even, it's never going to exceed the number like 4 or 5. So when you get things like the inverse Ackermann function or log star, which are other functions out there, they appear in some data structure analyses, such as disjoint sets. They grow so slowly but they're not as common as these ones. That's why I'm focusing on these ones. That's the point I'm getting at. Is that there's a lot more categories out there than just these ones, but these are the ones that if you talk to anybody in computer science, most people will know about these ones. But yeah, no, so let's start talking about using this definition of big O, okay, everybody? It's nice seeing some lovely, lovely love in the chat. By the way, like I said earlier, if you find yourself having any questions or anything like that, just drop it in the chat. I'm very happy to answer any questions, okay? So let's head on over there. We're going to start doing a bit of a warm-up with this so we can start getting a feel for how we can use this definition. So just remember the game plan. We got to find the two constants c and n0 such that f of n is less than or equal to c times g of n for all n greater or equal to n0. And you'll find very quickly that if you talk about different asymptotic notations, most of them have the same game plan. So that's why I'm only focusing on big O at this time, but I'll be talking about some other ones in the future. So just the big thing I really want you to get a grasp on from our definition is we need to identify those two constants, c and n0. And then on top of that, we also have to talk about how they have to satisfy this inequality we talked about. We have to show that c times g of n always dominates f after this point of n0 and on n0. So you're going to find that I'm going to give you a lot of little techniques you can use to make n0 very easy to pick. But the thing is, it isn't just as simple as that. You actually have to reason it out. Like I said, it's nice to be able to just pick out the two constants and say, here they are, suckers, I win. You can't just simply just do that, right? You have to show me why they work. Because that's much more meaningful than just give me the two constants. You also show me how I can figure them out for myself, too. It's the why. So that's why we try to formulate a game plan when we go and explore these things. So I thought it would be a good idea we try just using the definition of big O, and we're going to kind of run blind into this one, and we'll see what we get from doing this, okay? So let's do an example. Let's try proving. We're going to try proving that n squared plus 2n plus 3 is big O of n squared. So remember, when you see that fancy E symbol, I sometimes use that to say is, or is in. So, normally I'd like to say what I'm going to do, so usually a good way to start a proof off is maybe tell your reader what the heck you're doing. It's usually a good idea. So we compute the constants. We need to compute the constants. So we're going to find these two constants. So remember, the game plan is simple. We find the two constants. I want to reason to you why you can use these two constants. And then I'm going to be able to say, hey, look, here's C, here's N0. I'm going to present them to you. And if these are okay, invoke the definition of big O and you're done. That's the strategy we're going to use. So I'm going to compute these two constants. I'm going to explain. I'm going to usually pick one of the two first. Sometimes it's useful to pick one over another first. Sometimes you can pick both at the same time. There's not one hard or fast rule for doing this. You'll just find very commonly that C is the easier one to pick out of the two. But it doesn't necessarily have to be like that. So we compute constants C, which is a positive real number, and N0, which is a positive integer, such that for all n greater or equal to N0, we write out the inequality, right? We write out what f of n is, so that's it's n squared plus 2n plus 3, which is less than or equal to c times n squared, right? This is me just laying out what we're going to do. Because if I just just run head first into this, and I just start picking stuff, I don't know what you're doing, right? So I like to make sure, you can argue that, Dan, you're kind of telling me how I should write out a proof for this. Now, there isn't just one way to do this. This is just a suggested way of going about this. There's several other ways. But most certainly, a good strategy when you write out a proof is tell the reader what you're doing. That's usually a good place to start. So then what I'm going to do is I'm going to try picking a constant. Now, like I said, I'm going to just go blind into this. I'm just going to try to guess some number for C, okay? So I'm not kidding. I'm just going to guess one. I'm not going to pick a very smart one. I'm just going to guess one. So if I look at the left-hand side, you see I have an n squared, a 2n, and a 3. Notice that I can't pick C to be 1. Because if I pick C to be 1, notice that there's still 2n plus 3 right here. There's this right here. That means the left-hand side will still be larger if I pick C to be equal to 1. So what I'm going to do is I'm going to try picking C to be 2, and then we'll see what we can get for N0 from here. So I'm just going to kind of go into this blind, and we'll see what happens. We're going to pick C is equal to 2. Then now I'm just going to find N0, right? Then we find N0, so that for all n greater or equal to N0, we have n squared plus 2n plus 3 is less than or equal to 2n squared. Now, when I look at this, the first thing I'm going to try doing is try to get rid of the n squareds, or at least whatever I could do with the n squareds. I'm going to try to eliminate this to make this simpler. Usually that's a good place to start. Usually I like to say what I'm doing. If not, you trust your reader to understand what you're writing. So if you don't trust your reader to understand the steps you're using, elaborate. Usually that's a good strategy when you're writing out a proof. So I'm going to rewriting the inequality. Rewriting the inequality by subtracting. I was about to write subtracting by subtracting n squared plus 2 from both sides of the inequality. Both sides of the inequality. We get the following. So I'm just going to subtract that off of both sides. This is because I want to make it simpler for me to make some judgment call on what n0 should be. So what I'm saying is that n squared plus 2n plus 3 is less than or equal to 2n squared is for, and keep in mind, I have not specified a domain. I'm just rewriting the inequality. You have to be very careful when you write these things out, because notice that I'm not specifying when this is true or if this is true or anything like that. I'm just saying I'm rewriting the inequality. So this is no different. I'm using this back and forth arrow. This means if and only if, like I talked about earlier. So this double-sided arrow just means if and only if. It means that these are two equivalent statements. If and only if n squared minus 2n is greater or equal to 3. So I've subtracted n squared plus 2n from both sides. So notice that means that if you take n squared plus 2n, you subtract that from both sides, you'll have a 3 on one side, and then you'll have 1n squared left on this side, and then you'll still have the 2n on the other side. So now we have n squared minus 2n is greater or equal to 3. Now, you might say, Dan, it's obvious that n squared minus 2n is greater or equal to 3. That is a very impulsive thing to write right after this. Be like, Dan, that has to be obvious, right? Because that's a quadratic, that's a linear function, and that's a 3 over there. Well, certainly as n gets big enough, it'll be the case. Well, I don't want to quickly just say, obviously it's this, or clearly it's this. I want to give it the reason why that is the case. So I'm going to have to use a little bit more massaging to make this look a little bit more obvious to somebody that's looking at it. And I don't mean it as it's obvious as that's the reason. I'm trying to give a reason why this inequality over here has to be true for some value of n and on. So let's do that. And once we have that, we can get n0. But notice I'm just going like blind into this. You might ask, Dan, why did you pick that c? Well, like I said, I just wanted to make it kind of bigger, that it wouldn't get consumed by the left-hand side. But the issue with that is that I have to be more careful about n0's selection. I'm going to give you some tools for how to avoid this, so that it's easy as pie, not like the constant or something. I just literally mean like a very delicious pie, to come up with this result. So let's see what we could do about this. So next what I'm going to do is I'm going to factor the left-hand side of that inequality. Next, factoring the left-hand side. So I'll abbreviate this as LHS very often, of the inequality. Then that means that, notice I had n squared minus 2n, right? So if I have n minus 2 and I multiply this by n, I get n squared minus 2n, right? That's the same thing as me writing n squared minus 2n. And the right-hand side was 3, right? Well, I wrote it like this to make it easier for you to see what n0 should be. Because at first you might say, okay, well, what value of n works? Well, if you look at this very carefully, we're making kind of two presumptions here. First, I would like to make them as simple as possible. Now, I'm arguing to you that you can get even easier than just this for the way you pick the constants. But here, if you look carefully at this, look at this. Notice that for n greater or equal to 3, the left-hand side is strictly positive, meaning it's a strictly positive number. It's strictly positive. Why is this? Because, well, first, n itself is always going to be a positive integer, right? But notice here that if I pick n is 3 or greater, notice that it's going to be 3 minus 2 is 1, 4 minus 2 would be 2, 5 minus 2 is 3, and so on. This always will increase in its value because n may get larger, right? But the thing is, I would need to... Now, here's the neat thing. If I ensure I have n is greater or equal to 3, I can guarantee this fact, right? So this is strictly positive because n minus 2 is greater or equal to 1, and the product of a positive integer, I'm just going to abbreviate that, positive integer, with another positive integer is positive, right? But it's even better than that. I just don't have to say positive. I can say this is greater than 0. But here's the catch. Here's the catch. So now I know it's greater or equal to 0, right? But I could do even better than that. Furthermore, if n is greater or equal to 3, meaning I give you a number that's 3 or greater, notice that this n times n minus 2, this part right here becomes greater or equal to 1. Notice the n minus 2 now becomes 1 or greater. That means that if I plug in n, in this case, notice that that has to be greater or equal to 3. Because if I use n as 3, that's it right here, right? It'd be 3 times 1. There's 3 right there. Notice that if I have 4, it'll be whatever 4 is, so the input itself, times whatever the input is, minus 2. But remember, now this is bigger than 1. So most certainly 4 times a number that's bigger than 1, which 4 is greater than 3, right? Will only make an even larger integer, right? So this we get our key ingredient here, so we're just going to pick, we could pick n0 to be 3. So everywhere on 3 and after, you can guarantee that that inequality is going to get satisfied. Now, I must stress, like I said, that n0 could be 4, it could be 5, it could be 6, it could be 7, it could be 10,000 if you want it to be. Mathematically speaking, the M word, the dreaded M word, you can pick any one of these, but 3 is the smallest one that makes it easier for me to justify to you. Therefore, so now I'm going to, like I said, I got the two constants. I've shown you how you could come up with them. Now I'm just going to present them to you. I'm just going to invoke the definition of big O. So now I have the two constants, and I've checked them for you. Therefore, so remember, this isn't just some magic here. This is actually a part of the argument. So I gave you the two constants. Now you got to use the definition of big O to confirm it. Therefore, by selecting such C and N0, by the definition of big O, then we can have that n squared plus 2n plus 3 is big O of n squared. And we're done. Normally, I mark the end of the proofs with this box here. So this is just an example of me just going head first into this. Now, are there any questions about this example? Or is this pretty clear? So do you see how I can just like go by magic? The two constants work. I tried to justify the selections to you, but I'm using an argument to do this. I'm not just simply just wiggling my fingers and say, okay, pick C is 2 and pick N0 to be 3. I actually am trying to show you where those come from. If I pick one of them, I show you how to get the other one. Because as long as they exist, right? It's not that there isn't some magic two constants that always work. There might actually be a whole set of two constants that actually work. There might be whole sets of pairs of them. Sometimes there might only be one pair. There might actually be like a magic two that only work. There may actually be none if it is the case that f is not big O of g. But yeah, so what I'm going to show you is that it's actually a much easier way of going about this. So by the end of this session, you'll actually have a way of proving this without needing to pull out fancy tricks like this. And in fact, also, one other thing I want to point out to you is there's other ways you can derive these constants, like C and N0. You can use, for example, root solving techniques. So for example, you'll notice how I rewrote the inequality, right? Well, what if you treated this inequality like an equation and you try to solve for roots? Well, you would find, for example, that you might end up with the N0 that I have, but here's the catch. This is the big catch, is that you're all working on the presumption that whatever inequality you're playing around with will always be satisfied after that point. So you have to still have a reason for that. For example, you might say, oh, because the function is increasing, so on, so on, so on, so on. Use some calculus to justify this. If you define the complexity function by expanding its domain to, for example, to real numbers, or you define well, I technically speaking, you'd be okay still, but if you compute the, say the derivative and you show that one part of the inequality is always going to grow faster than the other, that's another way you could justify these things, but these are much more complex than just simply arguing things about products of numbers. Like, this is far more elementary. And very simple and easy things to justify are often your best friend when you want to convince somebody that doesn't understand what you're talking about. That's at least the way I like to view these things. You could use a sledgehammer if you want. I'm going to give you some simple ways to argue these things, but they do also exist. The other fault that you can run into with root solving approaches, which, like I said, you're more than welcome to use them, they exist, is that it also, like I said, there may exist multiple roots, and the question is, which one do you pick? Which ones do you pick? Works on the presumption that you know which one is the largest root you could pick. And you know that there's no other point afterwards, and you have to know about the shape of the functions. You have to know it always goes up, it doesn't come back down on one of the two. So, like I said, we want to keep it simple. But that's another way you could go about this. I'm not going to focus so much on that here. So, I'm going to show you a couple of crafty little ways you could approach these big O proofs, such that you don't have to pull up machinery like this, even. You can keep it even simpler. Now, with much more sophisticated functions, you may have to do more work than just even this. But most certainly, there exist other ways you can deal with things like polynomials that are in a much easier way. So, anyways, let me show you a quick little trick. And you're going to see that this trick is actually going to lead to a much more general rule we can actually come up with. And I'll include this proof. I'll give you a sketch of the proof in a moment. So I'm going to lovingly call this technique lookalike. So this trick I'm going to do is I'm going to call it a lookalike. So we're going to first try to exercise the idea of playing lookalike. And you're going to see what I mean in a moment. Okay, so we're going to try playing this idea of what we're going to call lookalike. So we're going to call this playing lookalike. And this works pretty well for a lot of simpler functions. Look alike. For some reason I wrote look able. That's kind of funky. Look alike. And the reason why I say that is that I want to come up with a function that's easy enough for me to describe to you, but when I pick out the constants, I want to make it mimic the left-hand side. So I want to make the right-hand side look alike the left-hand side. So that if I could get that so that either they're equal or greater on the larger side, presumably the c times g of n side, then we're done. But if I pick it in the appropriate way, I'm going to try to make it look very similar to what's on the left-hand side. That's the game we're going to play. So you know how we had that example earlier? Where I had 6n cubed and I told you it was big O of n cubed? We're going to do an example like this. So we're going to prove that 6n squared is big O of n squared. So we're going to prove 6n squared is big O of n squared using this lookalike approach. So remember the strategy I'm going to give you. So just a little bit of side work here. You know that we're going to have those two constants such that 6n squared is less than or equal to c times n squared, right? What I would like to do is pick the constant so that this looks alike the left-hand side. Does anybody see any interesting way to make it so the right-hand side looks like the left-hand side over there? So I want to make it look as close as possible to what's on the left-hand side. And what I'm going to do is I'm going to just pretend that the terms I have on the right-hand side, even if they were more dominant, meaning they're like higher exponents in them, I'm going to try to make it so it looks like the left-hand side. Whether I'm going to take terms, I'm going to spread them out, or I'm going to just simply try to make it so they look identical. You're going to see this is actually going to generalize into a very nice technique for how we can play around with inequalities. So I'll give you a bit of a tip here. Notice that if I make this a 6, notice that 6n squared is less than or equal to 6n squared. And notice that that means that this is an equality. It's not inequality, it's an equality. So let's use this idea. So as usual, I'm going to write out the game plan. We find constants. We find constants c and n0. Such that for all n greater or equal to n0, we have 6n squared is less than or equal to c times n squared. Based on the strategy I had suggested to you, we're going to pick c is equal to 6, right? We're going to pick c is equal to 6. Then we're going to find n0, right? Then we need to find n0 so that 6n squared is less than or equal to 6n squared for all n greater or equal to n0. I know it looks very obvious, right? At this stage, we're basically done, right? But I have to tell you, just saying it's obvious isn't an argument, right? That is you deflecting the responsibility of explaining to somebody why something is actually true. One tip it's a little bit of a story, but it's not really a story per se. But very often, at least for the kind of research I do and the kind of work I've done over the years, the most common places that people make mistakes is when they say something's obvious or it's just cuz. Those are the most like if they say it's obvious or clearly it's the case, these are the most common places people make mistakes when they're reasoning. So just avoid using I usually, when I write out proofs, I try to avoid using those terms unless there's a common understanding among the audience what clearly and obviously mean. I try to avoid using those terms. They're usually reserved for the most blatantly clear things that you could think of, like 1 + 1 = 2, or that n is less than or equal to n squared for all n is greater or equal to 1. So things like that at this level, those are what we would call obvious. So like this right here is pretty obvious, but because I want to give you a proof that gives you an explanation, I'm going to write out why that would be the case. So because I need to also tell you what n0 should be. So, well, for n greater or equal to 1, well, look, n is greater or equal to 1, so I'm specifying a domain for which the statement has to be true. Notice that this is an equality, right? It doesn't even need to be inequality, it's an equality. So I'm just going to say for all n greater or equal to 1, n greater or equal to 1, both sides of the inequality (6n squared is less than or equal to 6n squared) are equal, right? So I'm just going to choose n0 to be 1. That's the smallest I can pick it. Don't pick n0 to be 0. n0 is equal to 1. Therefore, now remember, now I need to pick up that definition of big O and use it. Therefore, by the definition of big O, big O, 6n squared is big O of n squared. And we're done. Piece of cake, right? Do you see how this lookalike approach? I didn't go head first into this. I could have picked, for example, 7 as C. I could have picked 8 as C. I could have picked 9 as C. But notice that 6 here is just pretty easy for me to identify because I tried to mimic the left-hand side. So I'm going to show you another example of this lookalike kind of approach. You can apply this for other kinds of functions too. Just be careful because when you jump from a polynomial to a logarithmic function, you have to be careful which one dominates the other when we talk about the sizes of the inputs of these functions. So let's do another example, just so you can get a flavor for what I'm talking about here. We'll get one with some multiple terms in there. And you will see that what we did at this first example here is actually a lot more work than we needed to do. And all it really is about comparing elements. That's really all I have to do. So let's do another example, everybody. So we're going to prove that n squared plus 12n is big O of n squared. Let's try doing this. Let's try this. Okay. So this looks kind of like my previous example, right? But notice now I have this plus 12n here. And the real question is what I do with that. Because one, I could just pick, say, for example, like C is 2, and I could get wherever, say, 12n gets beat by n squared at some point, right? I could do something like that in our first example, right? That's something actually we did before. That's fine. You can do that. But we're going to play this lookalike game again. So remember, I have n squared, and I have 12n. So I have two terms here on the left-hand side. Now, I have c times n squared at my disposal. So I get to pick what c is. So I have something that's going to look like n squared. And I have something that looks like an of n, but I'm only being able to operate with n squared terms. I would like to make it so that each of these looks like each one of these terms here. So notice that I have just one n squared there, and I have 12 n's right here. I'm going to try to match each one with an n squared. And like I said, n is less than or equal to n squared, right? It has to be that n itself has to be less than or equal to n squared for all n is equal to 1, right? So it doesn't matter that it's an n squared over there versus an n. I'm just going to try making them look like each other. And if I do this, it makes it easier for me to argue term-wise the truth of this inequality for some value of n and on. So this is going to be the game plan here. So let's do the proof. Again. So I'm going to say we need to find constants. So I first lay out the game plan. we need to find constants c, which is a positive real number, and n0, which is a positive integer, such that n squared plus 12n is less than or equal to c times n squared for all n greater or equal to n0. Now, if you look at my right-hand side here, up in my side work here, notice it's 1n squared, then I have a 12n squared. What should I pick for the constant c then? So I have 1n squared, I have a 12n squared. How many n squareds do I have? How many do I have? Do I have like 10 or 11 or 12? What do I got? Do I have 14? Do I have 15? Do I have 10,000? I have 13, right? I have 13 n squares sitting there on the right-hand side. So I'm going to pick c is equal to 13. Then I'm going to make an observation here, because I don't have a whole lot more I need to do. This is where I'm going to make my observation. Notice that for all n greater or equal to 1, so I'm making a statement about n greater or equal to 1. So for all n greater or equal to 1, the following is true. That n squared plus 12n is less than or equal to n squared plus 12n squared, which is equal to 13n squared, right? As the following is true. Now, I must stress that at this stage, I thought, oh, well, you could probably add a statement right here saying that we're going to find n0, but just for the sake of brevity with this example, I'm just going to cut it out, but I usually recommend you put the statement in there talking about how we're going to find n0 next. It makes the rest of argumentation a little more flow here, but I'm just going to keep it simple here. So now, you're going to see that this actually generalizes into a really nice argument, and I usually call this the bucketing approach. I don't know if there's any fancy name for it, but I'm going term by term, and I'm going to compare them just like I'm making lookalikes here. So notice that I have n squared, and I have an n squared, right? We know that n squared is less or equal to n squared. And this is true for all n greater or equal to 1, right? So we know that's true. This is, in fact, a true statement because they're equal to each other. But what about 12n? Actually, let me use a different color here. 12n versus 12n squared. Well, like I said, 12n is less than or equal to 12n squared, which if you really wanted to rewrite this, you could divide by 12 on both sides. You end up with n is less than or equal to n squared. Divide by n, you'll end up with n is greater or equal to 1, right? Because we're presuming we're working with positive integers. So that means that this is true for all n greater or equal to 1. So notice that this is true for n is greater or equal to 1. This is true for n is greater or equal to 1. What if I add these two inequalities together? So I add all the stuff on the left side, and I add everything on the right side to the right side. So I have n squared plus 12n squared on the right-hand side, and I have n squared plus 12n on the left-hand side. Because this is less or equal, this is true for all n is greater or equal to 1. This is true for all n is greater or equal to 1. If I lump these into two buckets, most certainly it has to still be true, right? Why? Because this is less or equal to this is less or equal to this. Right? And there's no way one is going to owe the other. Right? These are both positive. In fact, they're both going to produce non-negative numbers, right? So you can't make an argument that one of these is going to sap away value from the other, okay? You can't do that. They're only going to get either the same value or they're going to get bigger. So you can use this kind of argument. So notice that if I add this and this together, you end up with what we have right here, right? There's your first one, right here. The green stuff is this green right here. This stuff right here. So all it is just collecting things up into buckets, as we're going to see in a moment. So since this is true for all n is greater or equal to 1, then it means I could choose n0 to be choose n0 to be equal to 1. Therefore, by the definition of big O, then we could say that n squared plus 12n is big O of n squared. And we're done, everybody. We're done, everybody. Are there any questions about that example? I'm sort of leading us to where the kind of the underlying idea of this, what I'm calling the lookalike approach, leads us. We're going to see one more example like this so we get a real good mastery over how we are picking the constant c. Because the big thing that we're playing around with is c here. And notice that every example I've given you up to this point involves polynomials. But like I said, if these were logarithmic terms as well in here, you could also play this game too. Just you have to be careful when you're dealing with muddling around with different classes of functions. So I'm going to do one more example based on this idea, and it's going to generalize to the big idea I'm going to give you here shortly. So let's talk about this. So one more idea here. Well, one example. Okay. Okay, let's do another example here. So this is going to cement this idea a little bit more concretely. So we're going to prove that 4n to the power of 4. Now we're getting some larger powers here, but you're going to see it's not going to really matter much for us at first, because a lot of the time when you start seeing things like with powers with 4 and 5 and 8 and 20, people look at it like, I don't know how to evaluate that very quickly, except with a calculator or something. Don't worry. You're going to see that our lookalike approach is completely impervious to this idea. It's not going to spook us or anything like that. So we're going to prove that this function here is big O of n to the 4. So just keep in mind what I said about lookalike. We're going to try to make the right-hand side of the inequality that we're going to derive look like what's on the left-hand side, which is sitting right here. So let's write out the game plan. So we find constants. C, which is a positive real number. That's what this means. And n0, which is a positive integer. Positive integer. Such that the following is true for all n is greater or equal to 1. Such that for every n greater or equal to n0, it has to be the following. It has to be that 4n to the power of 4 plus 3n to the power of 3, 2n to the power of 2 plus n, or 1 times n to the power of 1, is less or equal to c times n to the power of 4. Now, does anybody have any good suggestions for picking the constant c? So what's a good choice for c? There's a lot of different ones you can pick, but based on what the strategy I've been laying out, there's going to be one that's a really easy one to pick. And it will work in a way that's very similar to the other example. Well, let's look at it. I could distribute the c times n to the power of 4. I can have 4 of those. I can have 3 of those, 2 of those, and then 1 of those. So I have 1 plus 2 plus 3, so that's 6, plus 4, that's 10. So I'm going to try picking c as 10, and let's see what happens with that. So I'm going to pick c as equal to 10, then we need to find n0 such that for all n greater or equal to n0, 4n to the power 4 plus 3n cubed plus 2n squared plus n is less than or equal to c times n to the power 4. So now, we're going to make the same exact kind of reason, okay? So we're going to use the same kind of reasoning I did last time. Except now instead of having just 2 terms, I'm going to have 4 terms. I know the cap of this makes it look like I have a 5th finger. I do have 5 fingers, but, well, sorry. I guess technically 5 digits, I guess, would be the better way of saying this. I don't know. We're doing big O stuff, okay? We're having a good time. So anyways, well, observe that 4n to the power 4 plus 3n cubed plus 2n squared plus n is less than or equal to 4n to the power 4 plus 3n to the power 4 plus 2n to the power 4 plus n to the power 4, which this is all equal to 10n to the power 4, right? For all n greater or equal to 1 as for the following reason. We're going to use the exact same trick we just used, and I'm going to illustrate this using buckets, okay? So let's head over here. We're going to lay out the reasoning for this. So remember the rationales, we're going to go term by term through each one of these. We're going to go term by term. We're going to compare the 4n to the power 4 against the 4n to the power 4. We're going to compare the 3n cubed to the 3n to the power 4, and so on. We're going to compare each one of these. So, as 4n to the power 4 is less or equal to 4n to the power 4. Remember, we could justify this for all n is greater or equal to 1 because they're equal, right? It's going to end up that if you simplify this out, you get 1 is less or equal to 1. For all n equal to 1. But here's the thing. Let's talk about this. Okay. Suppose that I have my 2 sides of my inequality. The one I wrote over there. We had each one of those. So imagine I have my left-hand side and my right-hand side. So every single time I introduce one term of some given power, like cubic or quartic or squared, etc., whatever it might be. When I have 4n to the power 4 compared against 4n to the power 4, I know that this inequality is true for all n is greater or equal to 1, right? So I could put 4n to the power 4s in the left-hand side, right? And for each one of those, I'm going to put 4 into this other bucket here. 1, 2, 3, 4. But I know whatever I put into this right bucket is going to always be either larger or equal to whatever quantity I put into the left bucket. So I can keep doing this, right? So notice that I have 4 here. So imagine that I'm, just for the sake of our discussion here, suppose I have 4 in here, and then I go to the next one where I have 3n cubed, right? So I have 3 of those I put in here. For each one of those, I put in a n to the power 4. So I put 3 of them into this bucket. And then I would put in 2 for each squared term, but then I would put 2 more n to the power 4s in here. And then I would put in my 1n, I put an n to the power 4 in here, and you would compare the two, you weigh the two. Well, most certainly, and if I have this many in here, and there's either equal or larger quantities in the right bucket, you can argue very clearly when I add over all of them, it has to be the case when I put them all together, right? This is why I refer to this as kind of a bucketing approach with the way I argue this. It's like lumping sums in buckets, then I add over them as I add over the inequalities. So I sum over the inequalities to make this reasoning work. So that inequality works over there because this is true. 3n cubed is less than or equal to 3n to the power 4. for all n greater or equal to 1. 2n squared is less or equal to 2n to the power 4 for all n greater or equal to 1. That r is looking a little sad. Let me fix that. And of course, I have n is less or equal to n to the power 4 for all n greater or equal to 1. Notice that all of these statements are true for all n is greater or equal to 1, right? That means that the overall inequality has to be true for all n is greater or equal to 1, because notice that when I add this to this to this to this, I add all 4 of these together, I end up with what I have over there on the board. And that gives us what we need to demonstrate the claim. So remember, the idea is that I'm adding everything from the left side, like these are all going in the left bucket. Then I have everything on the right-hand side. All of these are larger or equal to whatever's on their left-hand side, meaning that whatever's on the left-hand side has to be either smaller or equal to what's in the right bucket, okay? So that's what we're doing here. And that's really what's happening. That's actually everything we've done up to this point, believe it or not. Therefore, by choosing n0 is equal to 1, we found C and n0 and by the definition of big O, big O, 4n to the power 4 plus 3n cubed plus 2n squared plus n is in fact big O of n to the power 4. So that's the lookalike approach in a nutshell. That's at least what I call it. I call it the lookalike approach, because you're trying to make the right-hand side look alike the left-hand side, but you want to always do it such that everything on the right is going to be at least whatever's on the left-hand side. So that's the strategy of the lookalike approach. Are there any questions? So let me get the chat up here. Let me get that up. Okay. So is there any questions at all about the examples we've done up to this point? What I'm going to be doing next is I'm going to be going over how you could deal with polynomials. So I'll be starting off with a more basic way of proving this, with a much more restricted set of polynomials. But in the notes, I will include a full proof for when you have general coefficients for the polynomials. And I must stress that these are complexity functions. So keep in mind that they're always going to output something that is non-negative. But yeah, you're going to see that this lookalike approach actually generalizes. If we talk about polynomials, they will generalize to a general rule that you may have seen possibly in an algorithms class. I know I usually teach it to students. But I'll be showing a much more restricted version of the proof just for the sake of time, but the full proof with all the different coefficients being allowed to be negative or positive or 0. Ours will only have it where they're either 0 or positive, but the proof really doesn't change a whole lot. But I'll give you an idea of how you would go about it if you want to actually prove that claim. But I'll have that proof as well in my notes. I'm just moving the stuff for the buckets, okay, everybody? But I hope you're having a wonderful day so far. Yeah, we're going to talk about how we deal with polynomials, okay? And then after that, I was thinking we'll do a tougher example. And I think that'll be a good place for us to stop here today. But keep in mind that bigger example is going to be a lot more fascinating than all these other ones. I normally don't get a chance to talk about an example like this unless I really have time to do it. So if you're looking for something like to bite your teeth into, this is a really fun, like the last one we're going to do is a little bit more involved. So if you want to get your teeth into it, I'm actually showing you something that's actually a technique you could use involving called harmonic numbers in the harmonic series. It's actually a technique that's an analytical technique I'm actually going to use here. That's fairly easy to apply if you think of the bucketing approach. But the thing is, it actually is something you could do with some other types of analyses over, like if you're interested in sequences in series, for example. This idea of what we're going to do with that last example, like the final one I'm going to show you here today, that one actually you could use this trick to bound harmonic series. But we're going to need a discrete version of it. So it's going to be a little simpler. We're not doing anything with integrals or anything fancy-pantsy like that. I don't need to do any of that kind of stuff. We're living in the world of discrete stuff, so we don't have to do anything too fancy-pantsy like that. I'm going to drink a little bit of water here. Let me just get a little bit of water. Okay. I'm just going to erase the board here, and then we're going to get back on this. I must stress that those notes are mostly just me just making sure I'm writing down the correct things. It's mostly a prop. But like I said, those notes are available on Patreon, patreon.com/pagewizard. So all my resources are going to be available there that I go through here today, and also include other sessions for the Big O Bootcamp as well that I will be going through. There's other topics that are going to go into this, and I have some other things I'm working through as well. Sorry, I'm just getting really excited here. I know when students see what the look-alike approach that I show you gets into when you deal with polynomials, everything becomes a lot easier to play around with. So when we started off, we kind of just dove head first into finding the constants. I'm going to show you pretty much a recipe for dealing with any polynomial you like. So here, let's get on that. Okay. So let's talk about polynomials. So we're going to be interested in polynomials with the following form. Now I must stress that there's more polynomials than just these, but I will stress and I will give you a hint for how we can generalize the rule I'm going to show you here shortly. So consider the form P of n. So this function is going to be called P. It's going to have coefficients. The first one's going to be called a0. It's going to be multiplied by n to the k plus a1 times n to the k minus 1 plus a2 times n to the power of k minus 2 all the way down to a sub k minus 1 times n to the power of 1 plus a k n to the power of 0, which this right here is just 1, right? If you want to rewrite this in terms of summation notation, or you want this as a sum, it just looks like this. The sum from I is equal to 0 to k. So this is just representing each one of the terms. I'm just going to vary it over I. So I'll start off with I is 0, then I go I is 1, then I is 2, then I is 3, all the way up to I is k. You'll notice that this is actually just what I've written up here, is as follows. It's ai times n to the power of k minus I. So notice that when I is 0, you end up with a0 times n to the power of k. When it's 1, then you end up with a1 times n to the power of k minus 1. And when you put in k all the way at the end, you end up with ak times n to the power of k minus k, which is just 0 like we have over there. So this summation will be helpful for us for when we prove our claim here in a moment. But I must stress that these things, these multiplicative constants out front, these are called coefficients. Where coefficients a0, a1, all the way up to ak, these are all going to be non-negative, meaning that they're allowed to be 0 or positive. So I must stress that there is a way to generalize the approach I've stated as earlier. So I'm going to give you an approach for dealing with these kind of polynomials. and I'll tell you how you generalize the argument so that these are allowed to be negative. But I must stress it's still a complexity function, so the function still has to be as we defined it earlier. But like I said, the reasoning is very simple. So, like I said, you can have it where the coefficients are negative, but with just a small tweak of the argument I'm going to give you here, it's very easy to generalize. So the lookalike approach actually spells out an actual technique for dealing with polynomials that look like this. So do you know how we played lookalike, right? We had it where, okay, we tried to make it so we grouped the terms based on each polynomial, like each one of the terms that I have for the polynomial. And I tried to express it in that way. And I just added up those, and that's how I got C, right? That's actually the technique you can use with dealing with polynomials. So here's the theorem. So given constant, and I'm going to stress that for this proof, k is going to be an integer constant. It's going to be k is greater or equal to 0. But I must stress, by the way, that there's other ways you could also demonstrate that this also can be a real constant. But the proof I'm going to give you here only relies on it being integer-based. But like I said, there's properties out there you could easily extend this idea further. If you're curious about this, let me know. And the above coefficients the claim is that P of n, or P, well, I'll just refer to it as P here. P is big O of n to the power of k. That's the claim. So we're going to prove this claim now. And before I get to that, I want you to imagine that each one of these coefficients is like a light bulb. And I have a switch that I can use to include it or not include it. So keep in mind that any polynomial that I've given you in the past fits this form. You just have to pick out the constants for each one of the coefficients, right? So for example, earlier I gave you an example. I had 4n to the power of 4 plus 3n to the power of 3. We had 2n to the power of 2, and I just had n, right? Well, notice here that if you make k is equal to 4 in this claim here, you'll notice that this is actually going to have the same form, with the exception that I have nothing for the case of n to the power of 0. But wherever I have gaps like this, you can think of it like I'm turning off a light switch. But it isn't just any old light switch. It's a one that's variable, that I can control how much flow goes through. So you can imagine every time I toggle the switch on, it actually takes on the value of each one of these coefficients. So just like what we talked about earlier, when I pick out and I try playing lookalike, this is actually the same way this is going to play out. So let's do the proof here. So you're going to see that this bucketing approach I gave you in the past actually easily generalizes here. And you'll see very quickly that all of our examples are actually just special cases of this. And like I said, I'll give you a tip on how you would generalize this a little further, and I will have that proof in my notes. So, as usual, I give you the game plan. So we find constants. We find constants c, that's a positive real number, and n0, which is a positive integer, right? We find these two constants such that for all n greater or equal to n0, P of n is less than or equal to c times n to the power of k. Okay, so now I'm going to show you how I'm going to pick the constant. Now remember, all I did when I played lookalike with you earlier, in earlier examples, what I did was I looked at the coefficients of the polynomial and I just distributed the terms on the right-hand side to make them look like those ones, right? But what are those terms? Well, they're the coefficients of the polynomial, right? So I'm just going to pick C is equal to be A0 plus A1 plus all the way up to AK, which this is going to be equal to the sum from I is equal to 0 to K of AI. So I'm just going to take all those coefficients and going to add them together. And now remember, the way I picked the N0 before always ended up being 1. That's not a coincidence. It's because this actually is the case. It's going to be the case here. Then observe that for all n greater or equal to 1, well, let's write out what P of n is. P of n is that sum I have over there, right? The sum from I is equal to 0 to k of ai times n to the power of k minus I, right? Well, notice that every one of these terms, these n to the power of k minus I terms, as I gets bigger, it always makes this term smaller or equal to whatever n to the power of k is, right? So I'm going to do the same trick I did before. So watch this. So 0 to k, the sum from I is equal to 0 to k of ai times n to the power of k. So I'm just going to drop the minus I business. I'll just put a k right there. And then this is equal to the sum. So notice that all of these n to the power k's, they don't vary with I, right? So I'm just going to put it out to the side of the summation, and then look what you got sitting inside of here now. I is equal to 0 to k of ai. So I got all of this, then I multiply this by n to the power k. But what's that? What's this? That's C, right? That's C, exactly. So, but remember, this isn't enough. I have to still argue to you why this is the case. So you're going to notice very quickly that I can use the same set of reasoning that I did before, except it generalizes now. Now I have to do it over all of these terms inside the sum. I have to do it for each application of I. So I is 0, I is 1, I is 2, I is 3. But whenever it is the case that the coefficient is present. So when it's the case that AI is 0, I don't want to do this because you know that it's just going to be 0 versus 0, right? So as AI times n to the power of k minus I is less than or equal to AI times n to the power of k, well, notice that if I divide both sides by, well, let's take a look at this. We have k minus I, and I have a k there. Notice that if I take this and I chop off enough needed to make it so that that side over there, because I could divide both sides by AI, right? Because it's okay, because they're both going to be either, they're going to both be, well, if I presume they're not 0, right? This is very important, is that they're positive. So if they're both positive, I could just drop these, right? They could go away. Then I had n to the power of k minus I is less than or equal to n to the power of k. Well, look at this. If I take this and I divide both sides by whatever will make it so that I end up with a complete picture of this, in particular if I divide both sides by k minus I, if I divide by k minus I, in this exponent here. So remember, if I divide by k minus I here, with both sides, n to the power of k minus I divided by n to the power of k minus I is 1, right? So that means that n to the power of k over n to the k minus I, you should end up with whatever is left after you subtract off k minus I, right? But what is that? That's just I, right? Let's just check that for ourselves. Just some side work here. Let's see. K minus, so if I have k minus I, Okay, k minus k, these two are going to go away, but I have plus I left. So yeah, this will end up being just I here, right? So that means that this is going to be 1 is less than or equal to n to the power of I. But this is for all 0 is less than or equal to I is less than or equal to k with... So we want the ones where the coefficient is not equal to 0. And it is the case that this is for n is greater or equal to 1. If you actually look carefully at what I wrote here, this is just the exact same set of reasoning I've been using when we talk about bucketing the terms. It's the same exact idea. Make no mistake, this is the exact same kind of reasoning we were using before. I just divide the sides so that I could get the bigger one on one side, right? That's what I did every single other time, at least if you wanted to whittle it down further. So, choose n0 is equal to 1. Therefore, by the definition of big O, P is big O of n to the power k. And we're done. That's it. Surprisingly simple, right? It's surprisingly simple proof. It's just that it's actually just all of the things we've been doing up to this point thrown together into one cookbook way of doing things. So if you ever run into a polynomial with this form, you just simply add the coefficients. Now, you might say, Dan, what if my coefficients sometimes are negative numbers? Say, for example, like A2 is, say, -2 or something like that. Well, I'll give you an idea of how you do this. Well, the way this argument will work is that instead of it being where you just simply take each one of them separately, you'll take the absolute value of each one of these. And you'll notice that this argument actually just doesn't change a whole lot. So if this is P of n, so you have this, notice that putting the absolute value will make it either that if it's negative, it's only going to get bigger, right? If I drop the sign, it's always going to be positive. And then you'll end up with this right here. And you'd make an argument very similar to the one we had down here. But I will not go into those details too much here. But the general rule is if you're dealing with polynomials, you just take the absolute value of each one of the coefficients separately, you add those together, and then you could pick n0 to be equal to 1. Piece of cake, right? So that proof will be in the notes. So, that being said, that's everything I have to say about polynomials, but you can see very quickly that my example I gave here is actually very similar to the one I did just before. So if you find yourself looking at this proof and you're like, okay, Dan, I don't know what this is about, go back to the one we had just before this example and walk yourself through by plugging in the value of k and the coefficients. And you'll see that actually the reasoning we use is actually just an expanded version of what we just have right here. It's not any different. It's just that this is how you could deal with any polynomial. So are there any questions about that? Okay, that's great. Awesome, awesome. Oh, I appreciate the applause. So what I'm going to do, let me just switch back over here. What we're going to do is we're going to do one more example, and then that'll be the last thing I'm going to do here today. But this one is going to be a little bit more involved, which makes it a little bit more funky than the other examples I've done. So up to this point, we've just done some really basic examples. But I've been trying to give you some very simple techniques for how you could deal with these things without having to pull out any calculus or anything like that. It's very simple. So what I'm going to do is we're actually going to look at an example that uses what we call harmonic numbers, which itself, at first, when you first look at it, you're like, okay, so what the heck do I do with this? You're going to see very quickly that our example here is going to be a little bit wilder. It's where you're going to see that we're going to actually use a technique, and you actually run into this technique if you ever find yourself curious with what are called power series, or specifically, if you start dealing with something called a Taylor series, and sometimes you deal with things like harmonic numbers. Sometimes this technique I'm going to show you here gets used when you play around with harmonic numbers. You want to bound them appropriately. But yeah, I'll be talking about what a harmonic number is. I'll also be talking about what a logarithm is, if you've never heard what a logarithm is. If not, if you heard about it, that's great too. I'm just going to define a kind of a basic notion of it, and then we'll do a tougher example, which will connect the harmonic numbers with logarithmic functions, which is pretty slick. Let me just get a swig of water here, but hopefully having a good day so far, everybody. How's everybody doing, by the way? Hopefully having a good day. Hopefully having a good day. I got my Bootcamp hat on, okay? That's how you know we're in the zone, okay? But yeah, for polynomials, yeah, just you add the coefficients, but you have to take their absolute value. So if you're dealing with something like just as an example, say like 2n to the power 5 minus 2n or something like that. Yeah, something like this. Instead of it being where you add minus 2, you would add 2. And this will make it very generous. So I must stress as well that if they're negatives like this, it doesn't really matter to include them because it only makes the function's value smaller. It's just that it makes it handier because now you have a term against another term, which makes this argument go a little bit smoother. But that's the thing. It's about the argument. It's not about, like, because there's many pairs of values for these constants. Like you can have C and N0 be different values than the ones you get out of this. These aren't the only ones. It's just that you can most certainly go with these ones, and you can guarantee they always work, and you can use an argument just like this one. But what I'm going to do is I'm going to erase these boards, and then we'll get to our final example for today, okay? I'm really excited about this one, because it's a little bit more involved, and it'll get you thinking. So I'll go carefully through it. And here's the cool part. Here's the cool part. In a future session, what I'm going to do is I'm going to show you how you can even simplify it even further. So I'll be showing you some really neat techniques you can use from something called smoothness that you can use to actually make the analysis go even faster. Where it uses the same idea, except you never have to worry about one major issue that you run into with bounding these kind of sequences. Or in our case, bounding the values. It's like one big issue you run into very quickly is like, is the number evenly divisible by the other number? That's usually one big thing you run into that turns into a technical issue. And we end up having to do a little bit of bookkeeping around that in our example. There's ways to make it so that doesn't happen anymore. It's like you can just straight up just make an assumption. And this assumption is perfectly legal because the functions involved are called smooth. Or at least the one we're trying to prove the claim for is smooth. And you get some really slick results as a consequence of it. And sometimes people ask me, Dan, how do you assume like n is a power of 2 and you can kind of just keep going? It's because of techniques like these. But I won't be going through how you come up with that here. I'll be doing that in a future live stream at some point. I know that I'm planning to do kind of a mishmash of algorithms with some more of this analysis stuff. I'll also be doing some other fun topics. I'll be going back to some of my data structures lectures as well. So if you're wanting to learn a little bit about data structures, I'll be covering that. So I'll be going through all the fundamentals. And also I have a beginner programming series that I want to get back on because I sort of started it. I got up to a hello world and then it sort of just stopped happening for a while. So I need to get back on that. I know there's somebody that really wants to have that done. Because it's more that you could do in a Java program than just do hello world. I must stress that, by the way, that series isn't just like a hello world program. It's actually like about programming itself and why programming is a thing. So it isn't just simply that. It's actually about why we have programming languages and other things like that. It's built around if you have no background at all about programming. Like why we have programs, why do we have a lot of these ideas? And why do we need a programming language, or at least why would we want a programming language to deal with these things? Because if not, we have to like play in the land of communicating to the computer in pure bits and bytes, and that's not very fun at all. Oh, we got Spooky saying hi. Spooky, get over here. Get over here. Come say hi. Spooky, you saying hi? Everybody say hi to Spooky. Spooky the dog. Spooky wants to say hi to everybody. Spooky, come here. Come here. Come say hi. Come say hi. Come here. Come over here. You're kind of, you're just, your nose is on the camera. Come on. Come on over here. Come on over here, Spook. Spook, get over here. You just look like you're looking up, but it's just because... Okay. Okay, Spooky. Spooky, you gotta say hi to everybody. Okay, don't go that way. Okay. Spooky wants me to let her outside, so I'm gonna go let her outside, and then we'll come back and do our example. Okay, everybody? So let me just go quickly do that. Here, Spook. You want to go here? There you go. Now you go hang out there and behave yourself. Okay. Okay, I'm back. Let's get the camera on over here. Okay. Now we're going to get into some juicy stuff here, okay? It's okay. It's not too bad. It's not too bad. That I can tell you. Okay, so let's get in this. Just going to get a little swig of water again. Okay. So let's get on. So just as a preamble for our next example, I'm going to talk a little bit about logarithms and harmonic numbers. So I'll dedicate some more time to logarithms in the future. So let's first talking about logarithms. So I have a very basic question. So you can imagine this like as follows. So very often when I have a function, I give you the input, it produces output, like our machine at the beginning of our session. What if I asked you about the opposite? And in particular involving exponents. So here we go. So suppose I given some positive real number x. In fact, it could be technically 0. Yeah, it could be 0 as well. But I'll just keep it simple here for now. And b is greater than 1. Actually, let's make this non-negative. Let's make it non-negative. What power y is so that b to the y, actually no, it has to be a positive integer. I'm just thinking off the top of my head, it has to be a positive integer. It's equal to x. Y can be 0 though. Y can be 0. So this is really what we want to know about, is given x and b here, what power of y, so what should I make y to be such that b to the y is equal to x? So this is in contrast to the inverted question of this, which would be, I give you b and y and I want to compute what x is. I want to know what y you use to give me back x. So suppose, just for an example, suppose that b suppose we have powers of 2, just for sake of simplicity here. So let's source out some powers of 2, okay? So I got 1, 2, 4, 8, 16, and we could write this up to some power, to the power of n, for some n. So I could rewrite this to be 2 to the power of 0. I could rewrite 2 to be 2 to the power of 1. 4 is 2 squared. 8 is 2 cubed. And of course, 16 is 2 to the power of 4. And naturally, 2 to the power of n is just 2 to the power of n, right? If I ask this question to you, what should be down here at the bottom? If I were to look at this from left to right, what should be y in each one of these cases? So I have 2 to the what is equal to 1. I got 2 to the what is equal to 2. 2 to the what is equal to 4, and so on, right? Well, this would be 0, then 1, then 2, then 3, then 4, all the way up to n. So a function that describes y is called a logarithm. A function that describes y is called a logarithm. So the base of the logarithm, or what we have for our powers, so in our case we have powers of 2, this number here, this b, is referring to the base. So often when we talk about logarithms, it'll have some base. So very often we'll have it as base 2 in computer science circles. So it's a logarithm. That's an a in there. Let me just rewrite that. So just as an example, if I gave you log base 2 of 8, notice that, remember, like I said, 8 can be rewritten. So I have log base 2 of, that's just 2 cubed, right? So notice that the exponent here would be a 3. So 2 to the power of 3 is equal to 8, right? So notice that this is just simply asking, given the base, so base 2, this is the base down here, and given x, I want to know what y is. So this is what x is, and I want to know what y is. So notice y has to be 3 in this example. And another example, if, say, for example, I give you log base 2 of 1, what would be the result here? So it's 2 to the something is equal to 1. So what would that be? It's 0. So because 2 to the power of 0 is equal to 1. So if you have log base b of 1 for any one valid base, then the answer would be, sorry, that's not 0. No, yeah, it's 0. Yes. Sorry, I'm getting very excited here. Yeah, it is 0. Remember, 2 to the power of 0 is equal to 1. Yes. So now I'm going to define another thing for us. So we have logarithms here. And by the way, if you have any questions about logarithms, don't hesitate to bug me. I'm very happy to answer any of your questions. The other notion I need to define for you is what we call a harmonic number. That's the other piece or ingredient to this discussion. So harmonic numbers they're well known in series. Like if you talk about, say, a harmonic series, this is a well-known number sequence. But we're going to talk about the harmonic numbers. So given some n greater or equal to 1, the nth harmonic number which will be called h of n, is equal to the sum from I is equal to 1 to n of 1 over I, which this is just 1 plus 1/2 plus 1/3 plus 1/4, all the way up to 1 over n. That's what the nth harmonic number is. It's the finite version of the harmonic series. There's an infinite version of it as well, but it's just the nth or finite harmonic series. So, anyways, I must stress that in some circles, you'll see the nth harmonic number written like this, but for the sake of simplicity, I'm just writing it literally as a function like this, just for the sake of not needing to follow a convention, but for simplicity, I'm just writing it as a function directly, without having this cater to one community of how they would write the nth harmonic number. Okay, so here's the claim. This is the claim. We're going to prove that H is big O of log base 2 of n. This is what we're going to prove. You're going to see very quickly that this is going to be a little bit different than some of the other examples I've shown you. But at its heart is the same set of reasoning. So let's do the proof. So we find constants. Remember, we find the constants. That's what we're trying to say, what we're going to do. We find constants. We have a positive real constant, C, and a positive integer constant, N0. So that for all n greater or equal to N0, h of n, the nth harmonic number, is less than or equal to c times log base 2 of n. Now, we're going to have to deal with some cleanup here. Okay, so we have to be a bit careful about this. So the one thing we're going to watch out for is that we want to make it so that this nth harmonic number, I could try to make it and tie it to the next closest power of 2. So I'm going to try to round it up to something that looks like a power of 2 in relation to it. So I would like to make n, so now you might say I'm like doing with the harmonic number, but what I actually want to do is not actually that. I want to make n be rounded up to the next highest power of 2. So that when I talk about, you know how we had our example over here with the logarithms, where you'll notice that if I can get it so that the power of 2 is expressed literally like 2 to the power of n, notice that the result of the logarithm would be an n, for example. I'm going to try to do something like this to simplify your calculations. But it's a bit of bookkeeping. So to keep in mind that this is some bookkeeping. If we have some more analytical techniques, we can drop this entirely. But that'll be something I'll talk about in the future. That can actually simplify this analysis even further. So before this, before we do this, before we try to find C and N0, before we do this, let n be rounded up Now, if you're not sure what I mean by this, I'm saying that if I give you a number, if it isn't a power of 2, then if it's something that is, say for example, like 2 is in fact a power of 2, right? It's 2 to the power of 1. If I give you 3, notice that 3 isn't a power of 2, but 4 is. So what I want you to do is not round it down to 2, I want you to round it to 4. So I'm always going to round up. So I'm going to take whatever that number is, I'm going to make it so that it is in the form of the next highest power of 2. So for example, if I give you 5, I would like you to make it into something that looks like an 8. So I'm going to give another variable to give that as a name, okay? So I'm going to give a name to that. So let m be rounded up to the next power of 2. Next power of 2. So that m is going to be the name of that. M is going to be 2 to the power of log base 2 of n with the ceiling function. Now the ceiling function, for those that are not acquainted with this, it simply says, hey look, if I have, so I'm keeping this very simple. If I have a number like 2.3, I would like you to write it as 3 if you apply the ceiling function to it. If it's 2.001, you apply the ceiling function, it has to be a 3. If this was, say, 4.3, you'd make it into a 5. These are all examples. Just says, whatever you have, make it the next largest integer. If it is not an integer, make it the next largest one. So that's what this is doing, is it's just saying, okay, say for example, like I said, if I give you 3, well, 3, log base 2 of 3 would be something between 1 and 2, right? So that means that this will be something that will be like 1 point something something. So I'm rounding this up to 2, that make m equal to 2 squared, which is just 4. Okay? So that's what this is just doing here. And one thing I really want you to note is because I'm rounding up to potentially a larger number, if it isn't the power of 2, we can say right away that, note that n is less than or equal to m. And then another thing I'm going to do is another bookkeeping thing I'm going to do is I'm going to let k be equal to the ceiling of log base 2 of n. This is just to save some space. So just keep in mind that k is always going to be the ceiling of log base 2 of n. So just as an example, if I wrote that in the previous sentence, it would be that m is equal to 2 to the power of k. So these are just some 2 bookkeeping things that we're going to need for our analysis to keep this nice and slick. So now we get to the good stuff. And the following. And as follows. So let's watch what we got here. So now remember, I'm just going to write out what the definition of h of n is. So let's write out what that is. So h of n is equal to the sum from I is equal to 1 to n of 1 over I, which this, because of the way we defined it, right? It has to be that it's less than or equal to sum from I is equal to 1 to m of 1 over I, which this, if you think about it very carefully, is 1 plus 1 over 2 plus 1/3 plus 1/4, all the way up to 1 over 2 to the power of a something. What is the something? Well, it's m, right? So this would be 1 over m. But what's m? It's 2 to the power of the ceiling of log base 2 of n. But as we just established a moment ago, that this is just 2 to the power of k, because k is the ceiling of log base 2 of n. So this right here, just to be very clear, this is h of 2 to the power of k, because that's h of m. So just keep that in the back of your mind. So now I have this series, and I would like to do, so remember, I know that this is actually a relationship that h of n has with h of m. So now what we're going to do is as follows. I'm going to come up with a second series that's going to bound this one. And I'm going to do this very cleverly, and this is a common trick with dealing with harmonic series, is I'm just going to make it so that when I add parts of this sum, I'm going to do it like a bucketing approach like I did before. I'm going to use that bucketing idea I had to argue the size of the inequalities, but at the same time, I'm going to lump them into their own finite series. So watch this. Then we can formulate a second series as follows. And I'm going to do this on the right-hand side below. So watch this. So I'm going to take each one of these terms, and I'm going to group them in the following way. So watch this. And keep in mind, there is a way to formulate this in a discrete way. It's very easy to do, but the thing is, it really doesn't add anything to our exercise. So I'm not going to do that here. It's a lot more arithmetic than we need actually here. So I'm going to take each one of the terms I have here in this sum. Why? Because it's bigger than this, right? So if we can get something that involves this, and we can derive a c or something like that from there, then most certainly, if I find it for this larger sum, then most certainly it'll cover this one, the original one, h of n. So I have 1. So the first term right here is I have a 1. You can agree with me that 1 is less than or equal to 1, right? That's not too scary, right? Now I'm going to take the next two terms. So I'm going to take these next two terms. So I have 1/2 plus 1/3. Well, I'm just going to take 1/2, then I'm going to add another 1/2. So I'm going to compare 1/2 against 1/2, and I'm going to take 1/3 and I'm going to compare it against 1/2. Notice that 1/3 is less than, or in fact, it is less than 1/2, right? So I'm going to take each one of these terms, I'm going to take them in increasing powers of 2 many terms together, and I'm always going to write that by the next power of 2 that's on the right-hand side. Notice I have, this would be 1/1, this is going to be 2's in the bottoms, next one's going to have 4's in the bottoms, but I'm going to have 4 of them, then I'm going to have 8 of the 1/8's on the right-hand side, then I would have, and so on, it's like 16 of 1/16's, and so on and so on. So watch this. So the next one would be 1/4 plus 1/5 plus 1/6 plus 1/7. These are all going to be less than or equal to 1/4 because 1/4 is in fact larger than all of these ones, but it's equal to 1/4. So what I'm doing is I'm going to be bucketing everything on the left-hand side, which is this, and I'm going to have this new series on the right-hand side, which is going to end up being at least as big as whatever's on the left-hand side, okay? That's because each one of these is less than or equal to whatever's on the right-hand side, by the same reasoning we've used before. So notice that you can keep writing this out, and you'll end up with 1/2 to the power of k minus 1 plus 1/2 to the k power, 2 to the k minus 1 plus 1. But it's a plus 1, it's not part of the exponent here. I'm just giving you a general form for this. Plus 2 to the power of k minus 1. So notice it always goes up to, but not to the next power of 2 on the left-hand side. And then I just have here 1/2 to the power k minus 1 plus 1/2 to the power k minus 1 plus all the way to 1/2 to the k power minus 1. And this right here is done exactly to the power k minus 1 times. Then there's one last term I haven't accounted for. It's this one right here. Then I have 1/2 to the power of k. Sorry, it's getting a little small here. 1/2 to the power of k. This is less than or equal to 1/2 to the power of k, right? So now I have two buckets that I'm going to have. The left bucket and the right bucket. Notice everything on the left-hand side, when I sum all those, it has to be at least as big as my everything in the right bucket, okay? So, let's put it all together, and let's watch what happens. We're almost there, believe it or not. Because what's going to happen is we're going to put this all together, then we'll end up with something that will come back to our bookkeeping that we had earlier. And then they'll spit out C at us, and then we'll have N0. If we're clever enough. Keep in mind, like I said, we just need a C and an N0. I was about to say an N0. That's kind of weird. So, h of n is less than or equal to h of 2 to the power of k, which this is less than or equal to 1 plus 1/2 plus 1/2. That, remember, this is that I'm taking each one of those lines one after the other. So 1/2 plus 1/2, then I have 4 1/4, then I would have 8 1/8. So 1/2 to the power k minus 1 plus 1/2 to the power k minus 1 plus all the way up to 1/2 to the power k minus 1. Then I would have the plus 1 over 2 to the power of k at the end. But here's the cool part. I deliberately picked the things I did on the right-hand side. Do you notice anything interesting going on with these? So notice I have 2 1/2. I have 4 1/4. I will have 8 1/8. I'll have 16 1 over 16s, and so on. I have 2 to the power of k minus 1, 1 over 2 to the power of k minus 1s. These all sum up to 1. So that's a 1. This sums up to 1. This all sums up to 1. So I have 1 plus 1 plus 1 plus 1. But how many of these do I actually have? I have this plus 1 over 2 to the power of k, right? But that just means this is going to be, okay, it's 1, 2, 4, 8, 16. And I have this happening for each one of these. But notice it starts at, so I have 1, 2, 3, 4. But notice it goes up to k minus 1. But notice that it does this for each one of those. So it means it's going to be k plus, so I have k minus 1 many of those. Then I end up having this 1 here. And I have plus 1 over 2 to the power k. So notice I'm just adding up all the ones, how many there are. And I add 2 to the power k because that's the last term in this series, this finite series. Now, here we go. Here comes the bookkeeping, okay? Recall, k is equal to the ceiling of log base 2 of n. And n is less than or equal to m, which is equal to the power k, right? So now observe the following. Observe that for all n greater or equal to 1, that h of n is less than or equal to k plus 1 over 2 to the power of k, right? That's because we know this relationship between h of n and h of 2 to the power k. And then, well, what's k? K is the ceiling of log base 2 of n. Plus, well, 1 over 2 to the power of k, this is just 1 over m. Well, this, the ceiling of this, so if I round up log base 2 of n, it's either going to be a power of 2 or it's going to be 1 higher than that. So keep in mind, if this is a power of 2, it'll end up being literally this and it's an integer. Otherwise, it's a fractional number. It gets rounded up to the next highest integer. So I could cover this by bounding it so I can say this is all less than or equal to log base 2 of n plus 1. So I'm just going to add 1. So I must stress that this is together. I'm just adding 1 to cover this rounding up process. And now remember, n is less than or equal to m, meaning that I can replace the n here, sorry, the m there with n. But here's the thing. N is greater or equal to 1, right? So that means that 1 over n will never exceed 1. It'll always be 1, 1/2, 1/3, etc., etc. It could be any one of those. So that means this is all going to be less than or equal to log base 2 of n plus 1 plus 1. But what's this? This right here is just equal to log base 2 of n plus 2. That seems awfully simpler to play around with. So now the question is, okay, what do we do with this? So we're going to play the lookalike game, just like what we started off with. Okay, so now I have h of n is less than or equal to log base 2 of n plus 2. So what I need to do is I need to do something that makes this so that it's a little easier to play around with. Because remember, I need to get something like h of n is less than or equal to c times log base 2 of n. So notice that if I were to try to make this 2 look like a log base 2 of n, then maybe picking c is equal to 2 might be a good idea because it looks like something like this, right? I want something that looks like this. So I need 2 logarithmic terms to cover log base 2 of n and this 2 here. I could have picked c is equal to 3. That also works. But I'm going to pick c is equal to 2. Pick c is equal to 2. Then we find n0 so that h of n is less than or equal to 2 times log base 2 of n for all n greater or equal to 1. Well, let's put it all together. We got one last step and then we're done. Now, I'm going to take advantage of the fact that I know that a logarithm is an increasing function. So that's a fact that you can prove using induction or calculus. But I'm just going to take that as a fact, okay? It seems like a pretty reasonable thing for me to presume. Now, if you're not sure what I mean by increasing function, if you look at the shape of, if I plotted this out in a chart, the shape of a logarithmic function will look something like this, but it always goes up. It always goes up. It doesn't plateau. It doesn't go down. If I look at its chart, it only goes up. That's what we mean by an increasing function. So notice that when n is greater or equal to 4, h of n is less than or equal, remember that we established this earlier, log base 2 of n plus 2, right? H of n is less than or equal to log base 2 of n plus 2, which this, if we pick n is greater or equal to 4, I should also mention, and log is increasing. That's another reason what I'm doing here. This is less than or equal to log base 2 of n plus log base 2 of n. This is because log base 2 of 4 is equal to 2. So that's why I picked 4. It's because I needed to be big enough that it's equal to 2 or greater. So this is going to be at least log base 2 of 4, which is equal to 2. Which this is equal to, of course, well, log n. This is equal to 2 log base 2 of n. And we're done. So now I just have to choose n0. You'll notice that this is a different choice this time. This is because of the nature of the logarithmic function. There's one common pitfall students fall into, is they forget that the logarithmic function isn't a polynomial. It doesn't operate like that. You have to keep in mind what values it takes. So choose n0 is equal to 4, and then we can say therefore. So now we have seen n0. I'm going to present it to them. I'll say therefore by the definition of big O, h of n is big O of log base 2 of n. And that completes the proof. Very slick, right? And that concludes that example. Are there any questions? Any questions at all? Don't be shy. I'm really happy to answer any questions. But yeah, no, so the relationship, and this is something that you see very often when you work with the harmonic series, is the harmonic series has a relationship with logarithmic functions. And you'll find that often this relationship gets reflected very much in the way we analyzed the functions here. So if you're ever playing around with like infinite harmonic series, you'll find that there's some relationships they have as well here. And you'd use a technique that's very similar to the one I gave here. It's pretty slick. But I thought I would show you something a little trickier. So notice here that I'm using the same bucketing approach. That's the thing I really want you to notice, is that it's actually just the same trick I used before, except on a whole other dimension. Well, not mathematically speaking, not using that M word, but it's on another level, the way I use it. So that's why I wanted to finish off with that, because it's using the same techniques, it's just that we added this idea of the logarithm into the play here. And as I mentioned, that later on, so some point in the future, I will, and keep in mind, I do actually have this video on my channel right now. I'm just going to be redoing it though, because I want to improve the audio quality of some of these videos. Either way, I will be going through it live. is the idea of smoothness. What you can do, you'll notice I had a lot of bookkeeping about rounding up to the next highest power of 2. Well, if you have this idea of smoothness, it allows you to make a presumption like that n is a power of 2. And then you never have to worry about this bookkeeping at all, and you never have to worry about rounding up the logarithm at all. It actually makes the analysis go even smoother. Pun intended. And when you have that, then you can get different constants. They tend to be a little bit easier to derive that way. And you use the same technique. But yeah, no. So that's the that's a pretty neat place for me to stop. So in the future, I plan to cover things like more about properties of logarithms in relation to big O. I have stuff about smoothness, properties of big O. I will be going through all the standard proofs for properties of big O. I also am planning to go through recurrence relations. I should be talking about pretty soon about big omega and big theta. I know some students, for example, in the summers, they sometimes do analysis of algorithms classes. So sometimes knowing about big omega and big theta can be rather helpful. I haven't done videos on those, at least within this series. I haven't done that. But yeah, no. Are there any last questions? Don't be shy. I'm really happy to answer any questions. I guess I could take my hat off. I don't need this on anymore. The boot camp is over, guys, okay? But yeah, so if you're curious, I plan to do another gaming stream sometime later this week. At least that's my hope, because I'm planning to go through more Xenoblade Chronicles 2, because I need to finish that game up sometime soon. I plan to do some Monster Hunter Sunbreak, Monster Hunter Rise Sunbreak. But yeah, Big O Bootcamp, expect some more series that are live lectures like this. I plan to do ones on algorithm analysis, my Big O Bootcamp series, more on data structures. So if you're curious about any specific topics, I'm happy to cover it, okay? Specifically, and especially if you decide you want to support me on Patreon, because I do have ways to request things through that channel as well. But yeah, so you'll find that all the notes that I went through here today, they're all available on Patreon, patreon.com/pagewizard. So do it, and keep in mind that they are available at the supporter access tiers, which is just $5. It's really, it's like dead cheap. I'm trying to make computer science education more affordable for people. So I'm trying to break down those barriers, because I personally want to help as many people learn computer science without having to spend thousands upon thousands of dollars to get this stuff and it's done usually very mediocrity. Sorry, I'm getting very excited here. Done in a very mediocre way, and I'm not a big fan of that. Especially that these are what I consider very important theoretical computer science topics that usually don't get covered as well unless you have somebody that is dedicated to teaching this kind of stuff. I think of it as a parallel or alternative way to go about learning computer science, rather than the traditional route of going to university, or if you're at a university, this is a way you could self-enhance your studies. So, for example, some profs don't have time to go through examples to this degree. So you might find some of my examples or techniques rather helpful, especially if you're studying. But yeah, so I plan to be doing more live lectures like this. I am planning to do a combo or hybrid show. So for those that are watching, say on Twitch, for example, or on other platforms, I am planning in the future to do a show where it isn't just the live lecture. We'll actually have two components. It'll have a live component, where it's going to be a live lecture like this, but it'll be a shorter one. So it'll be something about half an hour to an hour tops. And then after that, it'll go to an intermission, and then we'll have a live gaming session. So that will be a hybrid show that I'm planning to do in the future. But right now, I'm kind of keeping these two separate right now, where I have the live lecture, and then I also have the gaming stream. So I'm doing both of them. I'm going to be doing more live lecturing as well. So hopefully you found something interesting to learn about this topic. If you're, say, a computer science student or interested in computer science, you might find some of this Big O stuff very helpful if you're doing any work in this kind of stuff. I'm trying to give you the recipes for success for studying Big O. But yeah, no, if you have any questions or anything in the future, feel free to reach out to me. I'm really happy to answer any questions. And other than that, I don't have any other questions. So I'm going to keep things rather straightforward here. And I'll say thank you very much for hanging on out. I want to say thank you, especially. Sorry, I'm just toggling around here, okay, everybody? I want to say thank you very much, everybody, for coming and hanging on out. I'll be doing some more live lectures here in the future, and as well, come and check out my other entertainment content here on the channel. So do follow, subscribe, tell your friends, come on out. We have a good time. We make computer science extra fun, but at the same time, learn and have fun, okay? So I want to say thank you very much, and have yourself a beautiful day. I'll see you later.